You might think the universe is fixed, like a painted ceiling of stars, but everything is flowing. Scientists once believed galaxies simply drifted apart in predictable patterns, like dots on an expanding balloon, yet careful measurements revealed something surprising. Entire regions of space drift together in the same direction, as if pulled by something hidden. This gentle current carries our galaxy and countless others across unimaginable distances, guided by forces acting far beyond what telescopes can easily see. Reality isn't as simple as it first appears, and astronomers have been surprised to discover these vast invisible influences shaping the motion of everything around us. In this video, we'll explore these cosmic currents and learn how they connect us to structures hundreds of millions of light years away. If you like these videos, I would appreciate if you clicked like or subscribed, as it's important for the channel and it helps others find it too, just like you did. Thank you. Now, let's get started. Gravity works in ways that can seem almost magical when you really think about it. Every single piece of matter in the universe, no matter how small, pulls on every other piece of matter. Your coffee cup pulls on distant stars, and those stars pull back. The effect is tiny, almost nothing, but it's there. When you scale this up to galaxies, things get interesting fast. Our galaxy, the Milky Way, contains hundreds of billions of stars. Each star has its own gravitational field. Put them all together, and you get something that can influence other galaxies millions of light years away. But here's where it gets strange. Astronomers discovered that galaxies don't just drift apart from each other the way you'd expect. They also have these extra motions, these little deviations that tell a deeper story. Think about a river flowing toward the sea. The overall current moves in one direction, but you'll also see smaller currents and eddies. Leaves floating on the surface don't just follow the main flow. They also get caught up in these local movements. Space works similarly. Galaxies ride the expanding universe like leaves on that river, but they also respond to gravitational currents we can't always see. Scientists call these unexpected motions peculiar velocities. The name sounds odd, but it just means the motion that's left over after you account for cosmic expansion. When they started measuring these peculiar velocities carefully, something remarkable emerged. Huge numbers of galaxies, spread across enormous distances, were all moving in the same direction. Picture standing in a field during a gentle breeze. Every blade of grass bends the same way. You can't see the wind itself, but its presence is obvious. That's exactly what astronomers found when they mapped galaxy motions across vast regions of space. Everything was drifting toward one particular area of the sky. The discovery happened gradually, through decades of careful observations. In the early 20th century, Edwin Hubble showed that the universe was expanding. Galaxies were moving away from us, and the farther away they were, the faster they receded. This became one of the pillars of modern cosmology. Space itself stretches, carrying galaxies along like raisins in rising bread dough. But as instruments became more sensitive, the picture grew more complex. Galaxies weren't just participating in cosmic expansion, they were also responding to local gravitational influences. Some moved a bit faster than expected, others a bit slower. These tiny differences held clues about the distribution of matter in the universe. Mapping these motions required incredible precision. Astronomers had to measure not just how fast galaxies were moving away from us, but also their sideways motions across the sky. Imagine trying to track the movement of a firefly on the other side of a football stadium. The technical challenges were immense, but the results were worth it. What emerged was a picture of cosmic flow. Galaxies weren't scattered randomly through space, moving in arbitrary directions. Instead, they formed streams and currents, all influenced by the gravitational landscape around them. And many of these streams seemed to converge toward one region. The area in question lies behind the plane of our own galaxy. The Milky Way is full of dust and gas that blocks our view of distant objects. Astronomers call this the zone of avoidance. It's like trying to see through a thick forest. The foreground blocks your view of what lies beyond. Despite this obstruction, The evidence for something massive in that direction kept mounting. Computer models suggested that only an enormous concentration of matter could produce the observed galaxy motions. We're talking about the gravitational equivalent of tens of thousands of galaxies worth of mass. The structure responsible for these motions earned a name that captures both its influence and its mystery: the Great Attractor. It sounds like something from science fiction, but it's a real gravitational feature of our cosmic neighborhood. Think of it as a vast congregation of matter, pulling on everything around it, across distances that boggle the mind. Distance in astronomy can be hard to grasp. The Great Attractor lies roughly 200 million light-years away. Light that left there when dinosaurs first appeared on Earth is just reaching us now. Yet across this immense gulf of space and time, gravitational influence still flows. It's a reminder that the universe is far more connected than our everyday experience suggests. The story doesn't end there, though. As observations continued and technology improved, astronomers discovered something even more remarkable. The Great Attractor itself appears to be part of an even larger structure. It's not the ultimate destination of cosmic flow, but rather a ray station in a much grander pattern. This larger structure has been called the Shapley supercluster. It contains thousands of galaxies organized into clusters and superclusters. The whole assembly stretches across hundreds of millions of light-years. It's one of the most massive structures known in the observable universe, and it seems to be the real source of the large-scale motions astronomers first noticed. Imagine discovering that your local river flows into a larger river, which flows into an even larger one, which eventually reaches the ocean. The cosmic situation is similar. Local galaxy groups flow toward larger clusters, which flow toward superclusters, which participate in even grander streams of matter. This hierarchy of structure reflects the way gravity works over cosmic time. Small density fluctuations in the early universe grew into larger ones. Matter clumped together in an intricate web of filaments and nodes. Galaxies formed where matter was dense, and they've been moving along this scaffolding ever since. The philosophical implications are intriguing. We often think of ourselves as isolated beings on a small planet, but we're actually participants in these vast cosmic currents. Our galaxy, our solar system, our world, all are being carried along by gravitational influences that span unimaginable distances. It raises questions about permanence and change. The constellations seem fixed and eternal from our perspective, but they're actually part of a dynamic flowing system. Everything is moving, everything is connected, everything responds to influences both near and far. Modern surveys continue to map these large-scale flows in ever greater detail. Projects with names like the Cosmic Flows Survey track the motions of thousands of galaxies. Each new measurement adds another piece to the puzzle of how matter moves through the universe. What they're finding is that cosmic flow is even more complex than initially thought. There are multiple attractors, multiple streams, multiple scales of organization. The universe looks less like a simple expanding balloon and more like a vast river system with tributaries, confluences, and delta regions. Some of these flows extend across truly stupendous distances. Galaxy motions suggest influences from structures so far away that we can barely detect them directly. It's as if we're feeling gravitational whispers from the edge of the observable universe. This connects to one of the deep mysteries of cosmology, the nature of dark matter. The visible matter in galaxies and clusters accounts for only a small fraction of the gravitational influence we observe. Something else, something invisible, makes up most of the mass that drives these large-scale motions. Dark matter doesn't emit or absorb light, so we can't see it directly. But we can map it by observing its gravitational effects. The large-scale flows that revealed the Great Attractor also help trace the distribution of dark matter across cosmic distances. In a sense, galaxy motions serve as a kind of gravitational seismology, revealing hidden structure through its influence on visible matter. The story of the Great Attractor illustrates how science progresses through careful observation and measurement. What began as tiny discrepancies in galaxy velocities led to the discovery of structure on the largest scales imaginable. It's a reminder that the universe often surprises us, revealing complexity and beauty in unexpected places. These discoveries also highlight our changing perspective on cosmic structure. A century ago, astronomers thought the Milky Way might be the entire universe. Today we know it's just one galaxy among hundreds of billions, participating in flows and currents that span appreciable fractions of the observable cosmos. The next time you look up at the night sky, remember that everything you see is in motion. The stars, the planets, the distant galaxies, all are participating in a grand cosmic dance choreographed by gravity across space and time. We're not just observers of this dance, we're part of it, carried along by currents we're only beginning to understand. We exist inside a galaxy that acts like a cosmic dust storm, obscuring our view of the universe beyond. The Milky Way wraps around us, filled with countless particles, gas clouds, and stellar debris that create a natural barrier to our observations. When astronomers point their telescopes towards certain regions of space, they encounter what resembles a thick, impenetrable wall of material. This cosmic obstruction creates what researchers have named the zone of avoidance. It's not that nothing exists in these directions, but rather that our own galaxy's dense disk blocks the light from whatever lies beyond. Imagine trying to observe a bustling city while standing inside a dense forest during a heavy snowfall. You might catch occasional flickers of distant streetlights, brief glimpses of movement, but the complete picture remains frustratingly hidden behind layers of interference. The challenge becomes even more intriguing when you consider that some of the universe's most massive structures happen to lie precisely in these obscured regions. It's as if nature has deliberately placed a curtain over some of the most important cosmic landmarks, forcing us to develop new ways of seeing. Radio waves became one of humanity's first tools for penetrating this cosmic fog. Unlike visible light, radio signals can slip through dust clouds and stellar interference with remarkable ease. Infrared observations followed, revealing heat signatures from objects that remain invisible to our eyes. These techniques slowly began painting a picture of what lurks behind our galaxy's dusty veil. What emerged wasn't a single, massive object, but something far more complex and distributed. The hidden regions contain vast networks of galaxy clusters, each containing hundreds or thousands of individual galaxies, all bound together by gravity across distances that stretch the imagination. These structures don't exist in isolation. They're connected by bridges of matter, creating a cosmic web that spans hundreds of millions of light years. The true scale of this hidden architecture becomes even more remarkable when we consider dark matter. Most of the universe consists of material that doesn't shine, doesn't reflect light, and barely interacts with ordinary matter except through its gravitational influence. This invisible substance outweighs all the stars, planets, and visible galaxies by an enormous margin. Think of dark matter as a vast, silent framework, underlying everything we can see. It forms invisible scaffolding that shapes how galaxies move and cluster together. When massive structures pull on distant galaxies, much of that gravitational influence comes from dark matter halos that can be many times more massive than the visible components. This invisible architecture works on timescales that dwarf human experience. Over billions of years, these gravitational influences guide the motion of entire galaxy groups, creating slow, steady flows through space. Our own Milky Way participates in this cosmic dance, drifting through the universe at hundreds of kilometers per second, carried along by gravitational currents we're only beginning to understand. The motion happens so gradually that it's imperceptible within human lifetimes, yet it's completely real and measurable. Every star in our galaxy, including our Sun, travels through space as part of this larger journey. We're all passengers on a cosmic vessel that's been sailing through the universe for billions of years, following gravitational currents that extend far beyond anything visible to the naked eye. Consider how water moves in a vast river system. Individual droplets might swirl and eddy locally, but the overall flow carries everything downstream towards distant destinations. Galaxies behave similarly, each having their own local motions and interactions, while simultaneously participating in much larger flows that reveal the presence of massive distant structures. These galactic currents don't rush or hurry. They represent a kind of cosmic patience that operates on scales almost beyond comprehension. There's something profoundly calming about this realization, that the universe organizes itself through gentle, persistent influences rather than violent, chaotic forces. The structures responsible for these flows aren't random or temporary. They represent fundamental features of cosmic architecture that have been growing and evolving since the early universe. What we observe today reflects billions of years of gravitational sculpting, as matter slowly accumulated into increasingly complex networks of clusters and superclusters. Modern observations suggest that what initially appeared to be individual massive objects are actually components of even larger structures. The universe seems to organize itself into a hierarchy of scales, with galaxies clustering into groups forming clusters, and clusters connecting across vast distances to create superclusters that span significant fractions of the observable universe. This hierarchical organization raises fascinating questions about the ultimate structure of space itself. Are there limits to how large these cosmic structures can grow, or do they continue expanding indefinitely? The answer touches on fundamental physics and the fate of the universe itself, reminding us that even our most distant observations connect to the deepest questions about reality. Motion flows through everything around us, from the tiniest particles spinning in their shells to massive collections of stars drifting across the cosmic dark. There's something deeply reassuring about this endless dance, knowing that even when everything feels frozen in place, countless movements continue at scales, both smaller and larger than we can easily imagine. The ground beneath our feet spins through space, carrying us along paths carved out billions of years before humans ever looked up at the night sky. Gravity shapes these journeys in ways that often surprise us. While the universe stretches outward, pulling galaxies apart like dots on an inflating balloon, other forces work against this expansion. Dense regions tug at their neighbors, creating currents that flow through the cosmic web. These competing influences mean that galaxies rarely move exactly as we might expect them to. Instead, they follow paths influenced by both the stretching of space itself and a gravitational pull of nearby matter. Our own galaxy participates in this complex choreography. The Milky Way belongs to a small family of galaxies, all bound together by gravity, and this family sits within a much larger neighborhood called a supercluster. For many years, scientists assumed they understood the forces guiding our motion through this region. They pointed to a massive cluster of galaxies, roughly 50 million light-years away, as the primary influence on our path through space. But measurements kept revealing something unexpected. When astronomers calculated how fast we should be moving, based on the pull from this nearby cluster, the numbers didn't match what they observed. Our galaxy seemed to be responding to something more distant, something with a stronger gravitational influence than anything they could easily identify. The motion suggested we were being drawn toward a region of space that appeared relatively empty when viewed through ordinary telescopes. This mystery deepened as more precise measurements became possible. During the middle decades of the last century, new techniques allowed scientists to map galactic motions with unprecedented accuracy. They could measure not just how fast galaxies were moving away due to cosmic expansion, but also detect the additional velocities caused by gravitational attraction. These extra motions, called peculiar velocities, revealed the hidden architecture of the universe. The detective work required patience and careful observation. Research teams spent years collecting data, comparing results, and slowly building a picture of how matter flows through our cosmic neighborhood. They tracked hundreds of galaxies, measuring their distances and velocities, looking for patterns in what initially seemed like random motion. The process resembled assembling a jigsaw puzzle where most of the pieces remained invisible. What emerged from this painstaking work was evidence of something remarkable: a gravitational influence so strong it could pull entire galaxy clusters across hundreds of millions of light-years. Yet this force seemed to originate from a region where no obvious source of mass could be seen. It was as if rivers of galaxies were all flowing toward the same distant point, drawn by something that remained hidden behind clouds of cosmic dust and intervening matter. The philosophical implications of such discoveries remind us how much of reality operates beyond our direct perception. We live surrounded by influences we cannot see, forces that shape our journey through space and time in ways we're only beginning to understand. The very ground we consider solid participates in motion so vast and slow that entire civilizations rise and fall while barely registering any change in direction. Back in the late 70s and early 80s, astronomers started noticing something strange about how galaxies move through space. These massive collections of stars weren't just drifting randomly in all directions, like you might expect. Instead, they seemed to be flowing together, almost like rivers converging toward the same destination. Picture thousands of galaxies, each containing billions of stars, all moving in roughly the same direction. It's as if some invisible force was gently pulling them along the same path. This discovery changed how we think about the universe's hidden architecture. Because random motion would make sense, but coordinated movement suggests something much more profound is happening. The challenge was that whatever seemed to be causing this galactic migration was hiding behind our own Milky Way galaxy. When you look up at the night sky, you're seeing through the disk of our galaxy, which is packed with stars and cosmic dust. All that material acts like a thick curtain, blocking our view of what lies beyond in certain directions. Astronomers call this obscured region the zone of avoidance. It sounds mysterious, almost like a place you shouldn't venture into, but really it just describes the practical problem of trying to observe distant objects through our galaxy's crowded disk. Imagine trying to watch a distant parade while standing behind a busy highway filled with bright headlights and thick exhaust fumes. What made this situation particularly intriguing was that the galaxy movement seemed to point directly toward this hidden region. It was like watching arrows all flying toward a target you couldn't see. The evidence was mounting that something extraordinarily massive was lurking in that obscured part of space, something with enough gravitational influence to affect galaxies across hundreds of millions of light-years. By 1986, researchers studying galaxy clusters in the constellations Centaurus and Hydra had pinpointed where this mysterious influence seemed to be coming from. They calculated that whatever was causing the galactic drift lay somewhere between 150 and 250 million light-years away, hidden behind our galaxy's disk. The scientists needed a name for this invisible gravitational powerhouse, something that captured both its immense influence and its mysterious nature. They called it the Great Attractor, a name that immediately sparked imaginations both in scientific circles and among the general public. It sounds like something from science fiction, a cosmic entity pulling entire galaxies toward itself. But the Great Attractor isn't a single massive object, like a giant star or black hole. Instead, it's a region of space containing multiple galaxy clusters, vast amounts of dark matter, and structures so enormous that they stretch our ability to comprehend scale. Think of it less like a single magnet and more like a gravitational neighborhood where several incredibly massive structures work together. One of the key components astronomers eventually identified is the Norma cluster, sometimes called Abell 3627. When they finally managed to observe this cluster using X-ray and infrared telescopes, which can see through cosmic dust better than visible light, they realized they were looking at one of the richest galaxy clusters in our cosmic neighborhood. The word cluster might sound modest, but these structures are anything but small. A single galaxy cluster like Norma can contain hundreds or even thousands of individual galaxies. Each galaxy itself contains billions of stars, so we're talking about astronomical numbers of stars, all bound together by gravity. But the galaxies are just the visible part of the story. These clusters also contain vast reservoirs of hot gas, much more massive than all the stars combined. The gas glows with X-ray radiation, creating invisible halos that extend far beyond the galaxies themselves. And then there's the dark matter, mysterious stuff that doesn't emit light, but provides the gravitational scaffolding that holds these enormous structures together. When you add up all the visible matter, the hot gas and the dark matter, a single cluster, like Norma, can weigh as much as quadrillions of suns. That's a number with 15 zeros after it, representing mass on a scale that's almost impossible to grasp. Yet even something that massive might not fully explain the motion patterns astronomers observe. The Great Attractor appears to be part of an even larger structure, a network of clusters and superclusters that creates what scientists call a gravitational basin. It's like a vast depression in the fabric of space-time, so large that galaxies hundreds of millions of light-years away feel its influence and slowly drift toward it. This raises profound questions about the nature of cosmic structure. We tend to think of space as mostly empty, with occasional islands of matter scattered throughout, but discoveries like the Great Attractor suggest that the universe is organized on scales we're only beginning to understand, with invisible threads of dark matter connecting distant regions and creating flows of matter across cosmic distances. The philosophical implications are staggering. Our entire local group of galaxies, including the Milky Way, appears to be part of a much larger cosmic current. We're not just orbiting the center of our galaxy, we're also participating in a vast migration that's been going on for billions of years. It makes you wonder what other hidden influences shape our cosmic environment, what other invisible attractors might be pulling us in directions we haven't yet discovered. The challenge of measuring things we can barely see stretches across millions of light years. Galaxies don't carry little signs telling us where they're headed or how fast they're moving. Instead, astronomers have to become detectives, using light itself as their primary clue. Light carries stories across the cosmos, and one of those stories involves color. When a galaxy rushes away from us, something fascinating happens to the light it sends our way. The light gets stretched out, like pulling on a spring, making it shift toward the red end of the spectrum. This red shift becomes a cosmic speedometer, telling us how quickly that distant island of stars is moving away from our own. Think of it like listening to a train whistle. As the train moves away, the sound gets lower, stretched out by the motion. Light does something similar, but instead of sound waves, we're talking about electromagnetic waves getting longer as space itself expands between us and distant galaxies. Scientists spent decades collecting these measurements, building vast catalogues of how fast different galaxies are moving. Slowly, patterns started emerging from all this data. Galaxies weren't just scattered randomly through space, moving in every possible direction. Instead, they seemed to flow together in streams, like schools of fish swimming through an ocean of darkness. These galactic streams all seemed to be flowing toward certain regions of space. One of those regions happened to be hidden behind a thick band of dust and stars from our own galaxy, making it nearly impossible to see what was pulling everything in that direction. This cosmic traffic jam of galaxies suggested something massive was tugging on them, something with enough gravitational pull to influence the motion of entire galaxy clusters. The discovery that galaxies form these large-scale flows changed how we think about the universe itself. Rather than being a random collection of stars and planets scattered through empty space, the cosmos turned out to be organized into enormous structures. Imagine a three-dimensional spider web, with galaxies strung along the threads, connected by invisible filaments of dark matter and separated by vast empty regions called cosmic voids. Gravity spent billions of years weaving this cosmic web, pulling matter into denser and denser clumps while leaving behind enormous empty spaces. The Great Attractor sits somewhere within this web, not as a lone monster hiding in space, but as part of a much larger landscape of mass and motion that extends far beyond what we initially imagined. Another piece of evidence for our cosmic journey comes from something called the cosmic microwave background. This is the faint afterglow of the Big Bang itself, radiation that fills every corner of space and carries information about the early universe. Most of this background radiation looks the same in every direction, but there's a subtle pattern hidden within it. When astronomers mapped this ancient light across the entire sky, they noticed something curious. One side of the sky appears just a tiny bit warmer than the other side, creating what scientists call a dipole pattern. This temperature difference is incredibly small, but it tells us something profound about our motion through space. Our entire galaxy is moving at roughly 600 kilometers per second relative to this background radiation. That speed might sound incredible by human standards, and it certainly is. But on cosmic scales, it represents more of a gentle drift than a wild ride through space. We're talking about a migration that takes hundreds of millions of years to carry us from one galaxy cluster to the next. The motion is so gradual that countless generations of stars are born and die during the journey. What makes this discovery so remarkable is how it emerged piece by piece over many decades. No single telescope or observation revealed the Great Attractor all at once. Instead, different groups of scientists using different instruments and different techniques slowly built up the evidence. Some studied optical light from distant galaxies, others looked at radio waves or infrared radiation. Computer simulations helped connect the dots between observations and theory. Each new piece of data added another element to the puzzle, until gradually a coherent picture began to emerge. Even today, that picture continues to evolve as more powerful telescopes and better computer models reveal additional details about how matter is distributed on the largest scales. The Great Attractor itself turns out to be just one part of an even grander flow of galaxies. And further observations revealed that our cosmic neighborhood is being influenced by structures even more distant and massive, including something called the Shapley supercluster. This enormous concentration of galaxies sits hundreds of millions of light-years away, yet its gravitational influence reaches across space to affect the motion of our own local group of galaxies. This realization transforms how we understand our place in the universe. The discovery wasn't just about finding a hidden object somewhere in space. It was about recognizing that we exist within an interconnected cosmic landscape, where the motion of our own galaxy is shaped by gravitational forces acting across distances so vast they challenge human comprehension. There's something both humbling and comforting in this perspective. For most of human history, people looked up at what seemed to be a fixed and unchanging sky. The stars appeared to hold steady positions, rotating slowly overhead as the Earth turned, but otherwise remaining constant and reliable. Now we know that everything is actually in motion, drifting through space along paths carved out by gravity, acting over cosmic time. Our Sun orbits the center of the Milky Way. The Milky Way falls toward massive structures like the Great Attractor, and those structures themselves participate in even larger flows and motions that span significant fractions of the observable universe. Yet despite all this cosmic movement, the night sky still appears peaceful when we step outside and look up. The stars shine with steady light, the air feels calm, and a sense of quiet settles over the landscape. The motion of galaxies unfolds too slowly for us to perceive directly, too gradually for us to feel, playing out over timescales that dwarf not just human lifetimes but the entire history of our species. This creates an interesting philosophical tension. We are simultaneously participants in one of the most dynamic processes in the universe, while experiencing it as perfect stillness and stability. Before we could ever map the vast cosmic structures that govern our universe, astronomers had to grapple with something far more subtle. There was this quiet, nagging feeling in the data, the kind that emerges when your measurements keep telling you the same strange story, over and over again. It wasn't the dramatic kind of discovery that makes headlines, but rather a gentle persistence, like water slowly carving through stone. The universe seemed to be whispering secrets, that something enormous and hidden was pulling on everything around us. Think about how we understand motion in our daily lives, how we expect things to move in predictable ways. When Edwin Hubble first showed us that galaxies were racing away from each other, expanding into the cosmic void, it painted such a clean picture. Space itself was stretching, carrying galaxies apart, like dots on an inflating balloon. In this elegant vision, once you accounted for that steady expansion, galaxies should mostly just drift along peacefully. Sure, there might be some local bumping around, neighbors tugging on each other gravitationally, but nothing too wild on the grandest scales. It's a bit like imagining raisins in rising bread dough, each one carried along by the expanding space around it. But the universe, as we've learned, time and again, rarely sticks to our tidy expectations. When astronomers started measuring galaxy distances and speeds with better precision, they noticed these little deviations. Some galaxies moved a bit faster than they should, others a bit slower, some seemed to drift sideways, compared to what the expansion alone would predict. These became known as peculiar velocities, which sounds almost whimsical, doesn't it? but the term carries precise meaning in astronomy. A peculiar velocity is simply how fast a galaxy moves, compared to what you'd expect from cosmic expansion alone. It's the signature of gravity's influence, both from nearby matter and from vast, distant structures we can barely see. At first, these peculiar motions didn't seem too surprising. Gravity has always shaped the cosmic landscape. Gravity has always shaped the cosmic landscape. Galaxies dance around each other in clusters. Clusters themselves interact and merge over billions of years. But as the measurements got better, patterns started emerging that stretched far beyond individual galaxy neighborhoods. Picture yourself standing by a wide, slow river, watching leaves drift on the surface. At first glance, each leaf seems to follow its own path, nudged by tiny currents and gentle breezes. But after watching for a while, you start to notice something. Many of the leaves are moving together, sharing a common drift that's almost imperceptible, but undeniably real. This is exactly the kind of pattern astronomers began detecting in the 1970s. Galaxy surveys of our local cosmic neighborhood revealed something remarkable. Galaxies within tens of millions of light years of us appeared to share a coordinated motion, as if our entire region of space was gently flowing in the same direction. The Milky Way itself provided one of the most important clues. Our galaxy isn't just sitting still in space, it's racing along at an incredible speed. Scientists can measure this by looking at the cosmic microwave background, that faint afterglow from the Big Bang that permeates all of space. When they analyzed tiny temperature variations in this ancient light, they discovered something startling. Our galaxy is moving at roughly 600 kilometers per second relative to this cosmic background. That's over 2 million kilometers per hour, a speed that would carry you from Earth to the Moon in less than 2 minutes. Yet this motion isn't chaotic or random, it's remarkably smooth and consistent, suggesting we're being pulled along a gravitational gradient toward regions of greater mass. Tracing the direction of this cosmic flow became a detective story spanning decades. By comparing the movements of many galaxies, astronomers could map the overall current of matter flowing through space. The trail pointed toward a region of sky in the direction of distant galaxy clusters, particularly Centaurus and Norma. At first, researchers thought the nearby Virgo cluster might explain much of this motion. Virgo is indeed massive, packed with thousands of galaxies and vast quantities of dark matter. Its gravitational influence certainly affects our galaxy and its neighbors in what we call the local group. But when they did the calculations, the numbers just didn't add up. Virgo's pull was significant, but not nearly strong enough to account for the observed velocities. The direction was slightly off too. Something much more distant, something far more massive, had to be contributing to this cosmic tug-of-war. This realization didn't arrive as a sudden eureka moment, but emerged gradually through the patient work of many astronomers. Science often moves this way, doesn't it? Not in dramatic leaps that transform our understanding overnight, but through careful accumulation of evidence, cross-checking results, refining measurements. It's like watching a photograph slowly develop in a darkroom, details emerging bit by bit until the full picture becomes clear. There's something almost philosophical about this process, the way truth reveals itself not through grand pronouncements, but through quiet consistency. Each measurement added another piece to a puzzle that was far larger than anyone initially imagined. The universe was teaching us that our local cosmic neighborhood, everything within hundreds of millions of light years, was part of something much grander. By the early 1980s, this pattern had become impossible to ignore. The evidence pointed toward the existence of something extraordinary, a gravitational influence so massive and so distant that it could pull on entire galaxy clusters, creating flows of matter on scales almost too large to comprehend. Looking up at the night sky, we see stars that appear perfectly still, frozen in their ancient patterns. But this stillness is just an illusion created by the vast scales of space and time. Every single point of light, every distant galaxy, is actually rushing through the cosmos at incredible speeds, caught up in movements so grand that they dwarf anything we experience on Earth. Think about a river flowing toward the ocean. Individual drops of water don't choose their direction. They simply follow the current created by the landscape around them. Galaxies behave in much the same way, streaming along invisible gravitational currents that stretch across hundreds of millions of light years. These aren't random movements either. They're part of something much more organized, much more purposeful. When astronomers first started measuring these galactic motions, they ran into a fundamental problem. Figuring out how fast something is moving requires knowing how far away it is, and measuring distances in space turns out to be one of the hardest things you can do in astronomy. It's not like you can just throw a tape measure across the void. Instead, astronomers have built what they call a cosmic distance ladder. For the closest stars, they use a technique called parallax, which measures the tiny shift in a star's position as Earth orbits the Sun. It's like holding your finger at arm's length and closing one eye, then the other, watching how your finger seems to jump back and forth against the background. The closer your finger, the bigger the jump. For more distant objects, astronomers rely on what they call standard candles. These are stars or explosions that always shine with the same intrinsic brightness. By comparing how bright they actually are with how bright they appear from Earth, you can calculate their distance. It's like seeing a candle in the distance. If you know it's a standard birthday candle, you can tell how far away it is by how dim it looks. Once these distance measurements became more precise, a remarkable pattern emerged. Galaxies weren't just expanding away from each other in the smooth, predictable way that the Big Bang Theory suggested. They were also streaming sideways, flowing along vast gravitational highways that nobody had expected to find. These bulk motions, as they came to be known, revealed something profound about the universe. Instead of being a collection of isolated island galaxies drifting randomly through space, everything was connected by an invisible web of gravitational influence. Entire regions of the cosmos, containing thousands of galaxies, were moving together towards some common destination. The scale of this phenomenon is almost impossible to grasp. A single galaxy like our Milky Way contains hundreds of billions of stars. A galaxy cluster might contain thousands of these galaxies. A supercluster can span hundreds of millions of light years. And yet, astronomers were detecting coordinated movements that extended across distances even larger than this. It was like discovering that entire continents on Earth were slowly drifting towards some distant shore. But here's where the story gets frustrating. When researchers tried to look in the direction where all these galaxies seemed to be heading, they encountered a major obstacle. That region of space lay directly behind the plane of our own galaxy, hidden by the dense clouds of dust and stars that make up the Milky Way. It was like trying to study a distant mountain range while standing in the middle of a thick forest. You could sense the mountain's presence from the way water flowed and wind patterns shifted, but you couldn't see it directly. This hidden region began to take on an almost mythical quality among astronomers. They could measure its gravitational pull, they could see its effects on thousands of galaxies, but they couldn't observe it directly. The invisible destination came to be known as the Great Attractor, though the name doesn't refer to a single massive object. Instead, it represents a gravitational center of mass, a region where matter has concentrated so densely that it pulls on galaxies across vast distances. The realization that our own Milky Way galaxy is caught up in this cosmic current was both thrilling and humbling. For centuries, humans had gradually learned that we weren't at the center of things. First, Earth wasn't the center of the solar system. Then, our solar system wasn't at the center of the galaxy. Now it turned out that even our galaxy wasn't stationary. It was just another passenger on a journey that began billions of years ago. There's something oddly comforting about this discovery. We often think of ourselves as fixed observers, watching the universe unfold from some stable vantage point. But in reality, we're all travelers, carried along by motions so ancient and so vast that they connect us to the deepest structures of the cosmos. Every atom in your body is participating in this grand migration, moving through space at hundreds of kilometers per second, without you feeling the slightest sensation of motion. The movements are so slow compared to human timescales that they unfold like a cosmic slow-motion movie. Even at these incredible speeds, it would take millions of years for a galaxy to move a noticeable distance relative to its neighbors. The universe operates on schedules that make geological time seem rushed. As astronomers developed better techniques for mapping galaxy positions across large areas of the sky, another piece of the puzzle fell into place. Matter in the universe isn't spread evenly like butter on toast. Instead, it forms an intricate cosmic web, with dense filaments connecting massive clusters while leaving enormous voids in between. Galaxies tend to line up along these filaments like beads on an invisible string, creating natural pathways for the large-scale flows that had been detected. Think of it like a three-dimensional highway system, with matter flowing along the filaments toward denser intersections. The strange motions that had puzzled astronomers weren't random after all. They were part of this larger pattern, reflecting the underlying architecture of space itself. This cosmic web provides the infrastructure for galactic migration, just as rivers follow the contours of landscape toward the sea. Galaxies follow gravitational gradients along these filaments toward regions of higher mass concentration. The Great Attractor turned out to be just one node in this vast network, part of an even larger structure that includes massive galaxy clusters and extends toward enormous concentrations of matter, like the Shapley supercluster. What started as a mystery about why galaxies weren't behaving as expected became a window into the universe's hidden skeleton. The strange motions were actually signposts, pointing toward invisible structures and unseen mass concentrations that shape the cosmos on the largest possible scales. They showed that the universe isn't just expanding uniformly, it's also flowing, streaming, and reorganizing itself under the patient influence of gravity. In a way, discovering these galactic flows was like learning that the ground beneath our feet isn't as solid as it seems. Everything we thought was permanent and stationary turned out to be part of something much more dynamic, much more alive. The universe revealed itself as a place in constant motion, where even the most massive structures are just temporary arrangements flowing towards some ultimate configuration that won't be reached for billions of years to come. Imagine trying to map something so enormous that light itself takes hundreds of millions of years to journey from one side to the other. This is the challenge astronomers face when they attempt to chart the gravitational landscape of our universe. We live within a cosmic architecture so vast that our minds struggle to comprehend its true scale. The universe presents us with a peculiar problem. Motion exists everywhere, yet we cannot simply watch it unfold like we observe clouds drifting across an afternoon sky. A galaxy might race through space at hundreds of kilometers every second, but from our perspective, it appears frozen in time. Over an entire human lifetime, that incredible speed translates to such a tiny shift in position that it remains invisible to our instruments. This reveals something profound about our place in the cosmos. We exist in a brief moment, a flash of consciousness trying to understand processes that unfold over billions of years. The patience required to map galactic motion extends far beyond any individual human experience. Astronomers have learned to read the universe like a detective story, gathering indirect clues rather than watching events directly. They measure properties of light, compare vast distances, and slowly build maps that reveal hidden patterns. It's similar to reconstructing the path of a river by examining the stones it has polished smooth over millennia. Before motion can be understood, distance must be established. This fundamental principle applies whether you're watching a car on a distant highway or observing a galaxy billions of light years away. Without knowing how far something sits from us, speed becomes meaningless, a number without context. The cosmic distance ladder represents one of humanity's most ingenious achievements. Each rung of this ladder works across specific ranges, and together they allow us to measure distances across the entire observable universe. It's a testament to human ingenuity, this ability to reach across impossible gulfs of space with nothing but careful observation and mathematical precision. For nearby stars, astronomers rely on parallax, a technique that exploits Earth's orbital motion around the Sun. As our planet travels its yearly path, nearby stars appear to shift slightly against the backdrop of more distant ones. This tiny shift, measured with extraordinary precision, reveals distance through simple geometry. Modern space telescopes can detect angles so small that they're like spotting a coin from thousands of miles away. But galaxies lie far beyond parallax range, requiring different approaches. Astronomers turn to standard candles, objects whose true brightness can be determined independently. Certain variable stars pulsate in predictable ways, their rhythm directly related to their luminosity. By comparing how bright these stars appear from Earth with their actual brightness, distance calculations become possible. It's remarkably similar to seeing a familiar streetlight across a dark field. If you know the wattage of that bulb, you can estimate distance based on how dim it appears. This simple principle, scaled up to cosmic proportions, helps us measure the distance to galaxies millions of light-years away. For even greater distances, astronomers rely on exploding stars called Typea supernovae. These cosmic explosions reach nearly identical peak brightness, regardless of where they occur, making them reliable markers across enormous distances. Each supernova becomes a cosmic lighthouse, briefly outshining entire galaxies and allowing distance measurements that stretch across billions of light-years. Once distances are established, the next challenge involves measuring galactic motion. This requires understanding redshift, one of cosmology's most powerful tools. Light behaves as a wave, and when its source moves away from us, that wave stretches like a rubber band being pulled. The amount of stretching reveals the speed of recession with remarkable precision. Most galactic redshift comes from universal expansion itself. Space grows larger everywhere, carrying galaxies apart like raisins in rising bread dough. The farther away a galaxy sits, the faster it appears to recede, simply because more expanding space lies between us and it. But sometimes galaxies move a bit faster or slower than expansion predicts, or even sideways relative to the general flow. This additional motion, called peculiar velocity, holds the key to understanding gravitational influences. When many galaxies in a region share similar peculiar motions, they're responding to the same massive gravitational pull, like streams converging toward a hidden valley. Large-scale galaxy surveys create three-dimensional maps showing not just where galaxies are located, but how they move relative to each other. These maps reveal the cosmic web, a vast network of filaments and voids that resembles neural pathways or the circulation system of some unimaginably large organism. Matter flows along these filaments toward denser regions, following paths laid down by gravity over billions of years. Creating such maps requires patience and technological precision. Telescopes scan enormous areas of sky, recording positions and redshifts one galaxy at a time. Slowly, observation by observation, these measurements build into comprehensive charts showing the universe's large-scale architecture. One significant challenge involves regions hidden behind our own galaxy's disk. Dust and gas in the Milky Way absorb visible light, obscuring distant galaxies like fog, concealing a mountain range. But light comes in many forms beyond what our eyes detect, and each wavelength reveals different aspects of cosmic structure. Infrared observations penetrate dust more effectively than visible light, unveiling galaxies that would otherwise remain hidden. Radio telescopes detect emissions from neutral hydrogen gas, revealing galactic positions even when stars cannot be seen. X-ray telescopes observe hot gas filling galaxy clusters, often glowing brightly even when individual galaxies blend into the background. This multi-wavelength approach resembles exploring a landscape in thick fog, using not just sight, but also sound, touch, and careful measurement. Each sense contributes information that others miss, gradually building a complete picture of otherwise inaccessible terrain. The Tully-Fisher relation provides another elegant tool for distance measurement. This method exploits the connection between spiral galaxy rotation speed and luminosity. Faster spinning galaxies tend to be more luminous, creating a relationship that can be calibrated and used for distance estimation. By measuring spectral line widths that reveal rotation rates, astronomers can determine true brightness and calculate distance independently of redshift. This technique proves especially valuable for studying galaxy flows, because it provides distances that don't depend on motion toward or away from us. Comparing redshift-derived velocities with distance-based expectations reveals peculiar velocities, tracing how galaxies move relative to universal expansion. The methods astronomers use to map cosmic motion reflect something deeper about human nature and our relationship with the unknown. We are creatures of brief lifespans trying to understand processes that unfold over cosmic time. Yet through patience, ingenuity, and careful observation, we gradually piece together the universe's grand design. One measurement at a time, scientists have spent decades gathering measurements from distant galaxies, noticing something peculiar in the data. Galaxies spread across enormous regions of space seem to move in the same general direction. It's almost as if they're rolling down invisible hills in some vast landscape made of gravity itself. When researchers started mapping these movements, they created something like weather maps, but instead of showing wind patterns, they showed galaxy flows. Arrows and streams on these maps revealed currents of motion, all converging toward certain mysterious regions of space. The patterns suggested that something massive was pulling on everything around it. One of the most reliable ways to study these cosmic movements involves looking at the faintest light in the universe. The cosmic microwave background radiation fills every corner of space, providing a kind of universal reference point. It's remarkably uniform across the sky, which makes it perfect for detecting motion. When our galaxy moves through space, it creates a subtle temperature difference in this background radiation. One side of the sky appears slightly warmer, the other slightly cooler. One side of the sky appears slightly cooler. This effect, called dipole anisotropy, works like a cosmic speedometer. It tells us exactly how fast we're moving and in which direction. The measurements reveal something remarkable. Our entire local group of galaxies, including the Milky Way, is racing through space at hundreds of kilometers per second. We're part of a massive flow, carried along by gravitational forces operating on scales that dwarf our everyday experience. Computer simulations help make sense of these observations. Modern supercomputers can model the entire universe, starting from conditions just after the Big Bang. They let gravity work on virtual matter for billions of simulated years. Watching as structure slowly emerges, these digital universes develop patterns strikingly similar to what telescopes actually observe. Filaments of matter stretch between massive clusters, creating a cosmic web. Galaxies flow along these structures like water, flowing through invisible channels carved by gravity. The simulations also reveal how much invisible matter must exist to create the movements we see. Dark matter, which doesn't emit or absorb light, makes up most of the universe's mass. Its presence can only be detected through gravitational effects, but those effects are everywhere. Galaxies spin faster than visible matter alone can explain. Galaxy clusters hold together more tightly than expected. Large-scale flows require enormous concentrations of unseen mass to drive them. Dark matter provides the missing ingredient, the hidden scaffolding that shapes cosmic architecture. There's something almost meditative about how this understanding developed. No single observation provided all the answers. Instead, knowledge accumulated gradually, like sediment settling in layers over geological time. Distance measurements, galaxy surveys, infrared observations, radio astronomy, each method contributed small pieces to an enormous puzzle. The work unfolds with a patience that modern life rarely allows. Astronomers spend careers refining measurements, building better instruments, collecting data that might not reveal its secrets for decades. Each new observation adds detail to maps that will never be complete, because the universe itself continues to evolve. From our tiny vantage point on Earth, we've learned to trace the motion of structures spanning hundreds of millions of light years. We've discovered that galaxies don't wander randomly through space, but follow paths carved by gravity, acting across distances that challenge comprehension. Modern telescopes continue expanding these maps, revealing ever larger structures and more subtle patterns of motion. What once seemed like isolated phenomena now appear connected, part of flows that span significant fractions of the observable universe. The Great Attractor, that mysterious concentration of mass pulling on our local group, no longer seems like a single object. Instead, it appears to be one node in a vast network of matter, connected to other massive structures through filaments and flows that operate like a cosmic circulatory system. Galaxy motions that once puzzled astronomers now fit into grander patterns. The movements represent slow migration through landscapes of gravity that took billions of years to form. These are valleys and peaks not made of rock or soil, but shaped from the fundamental forces that govern matter and energy. If we could somehow step outside our normal perspective, we might see galaxies drifting along gentle slopes in this gravitational terrain. Their motion is unhurried, almost peaceful, unfolding over timescales so vast that entire civilizations could rise and fall without witnessing any noticeable change in direction. The maps we've created represent one of science's most ambitious projects, an attempt to chart the invisible architecture that underlies everything we can see. They reveal a universe far more structured and interconnected than early astronomers ever imagined, where motion and matter dance together in patterns of almost incomprehensible beauty and scale. Imagine standing in your backyard, looking up at the night sky, and seeing that faint, cloudy ribbon stretching across the darkness. That's the Milky Way, our home galaxy, appearing as delicate as gossip caught in moonlight. But here's the thing. What looks gentle and transparent to your eyes is actually one of the most effective barriers in astronomy. It's like nature's own curtain, hiding some of the universe's most important secrets. The Milky Way contains hundreds of billions of stars, all packed into a disk shape that's remarkably thin compared to its width. Think of it like a cosmic pancake, maybe 100,000 light-years across, but only a few thousand light-years thick. We're sitting inside this pancake, about halfway between the center and the edge. When we try to look through the thick part, through all those layers of stars and dust, it's almost impossible to see what's on the other side. Astronomers have a name for the parts of sky where this blocking becomes severe. They call it the zone of avoidance. It sounds dramatic, almost like something from science fiction, but it's really just a practical description. When you make maps of where galaxies are located, there's this broad stripe where hardly any galaxies show up. Not because they aren't there, but because we simply can't see them through our own galaxy's clutter. The real culprit here isn't just the stars, it's the dust. Interstellar dust consists of particles smaller than smoke, tiny bits of carbon and silicon drifting through space. These microscopic specks are incredibly good at absorbing and scattering light. When light from a distant galaxy travels through clouds of this dust, most of it never reaches our telescopes. The galaxy is still there, shining as brightly as ever, but from our perspective, it just fades away. For early astronomers using optical telescopes, this created a frustrating puzzle. They could measure the movements of galaxies, detecting strange motions that suggested something massive was pulling on them from a particular direction. But when they pointed their telescopes toward that very direction, they saw almost nothing. It was like feeling a strong wind coming through a closed door without being able to see the storm on the other side. This invisible influence became known as the Great Attractor, a mysterious concentration of mass that seemed to be tugging on galaxies across hundreds of millions of light-years. The irony was perfect. One of the most significant gravitational influences in our local universe was hidden behind the very galaxy we live in. Looking through the plane of the Milky Way is like trying to study distant mountains while standing in a thick forest at night. The trees around you are close, numerous and bright, and they block your view of everything beyond. But imagine if you could suddenly see through those trees, using different kinds of light that the leaves couldn't stop. That's exactly what happened when radio astronomy developed in the 20th century. Radio waves have much longer wavelengths than visible light, and dust particles that easily block visible light are almost transparent to radio waves. Deuteral hydrogen gas, which fills galaxies throughout the universe, emits radio waves at a very specific wavelength, 21 centimeters. By tuning their radio telescopes to this frequency, astronomers could detect galaxies even when they were completely invisible to optical telescopes. It was like discovering a hidden city by listening for the distant hum of traffic through fog. Gradually, radio observations began revealing galaxies and structures that had been concealed for decades. The zone of avoidance wasn't empty. After all, it was full of the same kinds of cosmic architecture found everywhere else. Infrared astronomy provided another breakthrough. Infrared light, which sits just beyond the red end of the spectrum our eyes can see, penetrates dust far more effectively than visible light. Space telescopes designed to observe infrared wavelengths began uncovering galaxies and clusters in regions that had seemed nearly barren. Each new wavelength of light was like gaining a different kind of vision, allowing astronomers to see through the cosmic dust in ways previous generations never could. X-ray observations added yet another layer of understanding. Galaxy clusters contain vast amounts of extremely hot gas, heated to millions of degrees, and this gas glows brightly in X-rays. Space-based X-ray telescopes could detect this emission even when optical observations were impossible. By mapping X-ray sources in the direction of the zone of avoidance, astronomers identified massive clusters and confirmed the presence of enormous concentrations of matter. Piece by piece, the hidden landscape began to emerge. Among the structures revealed was the Norma cluster, one of the richest galaxy clusters in a nearby universe, comparable in mass and size to famous clusters that had been studied for decades. Yet it had remained largely unnoticed, simply because it lay behind the dense plane of our own galaxy. The Great Attractor itself turned out to be part of something even larger, a network of mass concentrations extending across vast distances. What had seemed like a single, mysterious influence was actually part of the universe's web-like structure, with filaments and clusters stretching across hundreds of millions of light years. There's something almost philosophical about this story. Here we are, embedded within our own galaxy, and that very fact, the thing that gives us a front row seat to stellar phenomena, also creates one of our biggest blind spots. It's a reminder that perspective shapes everything we can know about the world. Sometimes the things closest to us are the very things that prevent us from seeing the bigger picture. Even today, mapping the region behind the Milky Way remains more challenging than studying other parts of the sky. Observations must be carefully corrected for dust effects. Distinguishing distant galaxies from foreground stars requires sophisticated techniques. The dust doesn't absorb all colors of light equally, so astronomers must account for how it changes the apparent brightness and color of objects seen through dusty regions. Despite these challenges, modern surveys combining multiple wavelengths have revealed that the region behind our galaxy is rich with structure. Clusters and filaments extend across enormous distances, shaping the motion of galaxies throughout our cosmic neighborhood. What once seemed like an empty zone has become one of the most interesting regions for understanding how mass is distributed on the largest scales. The zone of avoidance teaches us something profound about the nature of discovery. Sometimes, the most important things are hidden in plain sight, blocked not by distance or exotic physics, but by the simple fact of where we happen to be standing. Our own galaxy, beautiful and vast as it is, creates shadows that stretch across our understanding of the universe. The universe reveals its secrets slowly, like a patient teacher waiting for us to develop better eyes to see. When we look toward certain regions of the sky, dense bands of dust and stars in our own galaxy block our view, creating what astronomers call zones of avoidance. These aren't empty spaces, they're simply hidden from us by cosmic dust and debris floating between the stars. Think of it like trying to see through a thick forest. The trees closest to you block your view of the distant mountains, but that doesn't mean the mountains aren't there. As our instruments improve, as our methods become more sophisticated, these hidden regions slowly come into focus. Each new telescope, each new technique, peels back another layer of the cosmic fog. The process resembles assembling a jigsaw puzzle in poor lighting. At first, you can only make out a few pieces here and there. The overall picture seems hopelessly incomplete, but as someone gradually turns up the lights, more pieces become visible, patterns start emerging, and what once looked like chaos begins to make sense. This gradual revelation carries a profound lesson about the nature of knowledge itself. What appears invisible isn't necessarily absent. It's often just waiting for us to develop better ways of looking. The universe doesn't intentionally hide things from us. We simply haven't learned how to see them yet. Even now, these hidden regions aren't fully mapped. New surveys continue to find galaxies tucked away behind cosmic dust, each discovery helping astronomers piece together a more complete picture of our cosmic neighborhood. Every new observation refines our understanding of how matter is distributed through space, how gravity shapes the architecture of the universe. For decades, if you asked an astronomer to describe our galaxy's address in the cosmos, they would give you something like a cosmic mailing address. The Milky Way, they'd say, belongs to the local group, which sits within the Virgo supercluster. This description worked well enough. It provided a sense of order, a hierarchy that felt familiar, like describing a house on a street in a town, within a county. But as observations became more precise, as galaxy surveys expanded their reach, this tidy picture started showing cracks. The Virgo supercluster, once thought to be a clearly defined structure, turned out to be just one piece of something vastly larger. The boundaries weren't where astronomers thought they were. This realization triggered a fundamental shift in how we think about cosmic structure. Instead of focusing solely on where galaxies sit in space, astronomers began paying attention to where they're going. Motion, it turns out, reveals patterns that static positions alone cannot. Imagine standing in a landscape of rolling hills and deep valleys, but everything is shrouded in such thick fog that you can't see the terrain around you. You might think you're lost, unable to understand the shape of the land. But if you watch carefully, you might notice streams of water flowing past your feet. Even without seeing the hills themselves, you could map the slopes by following these streams. Water always flows downhill, and by tracing its path, you can reconstruct the invisible landscape. Galaxies behave remarkably similarly. They drift along gravitational gradients, flowing like cosmic rivers toward regions where more matter has accumulated. By mapping these motions across vast regions of space, astronomers can identify gravitational basins, enormous areas where everything flows toward a common center. In 2014, researchers used this approach to completely redefine our cosmic neighborhood. By analyzing how thousands of galaxies move through space, they identified a colossal region where galaxies share a common flow, all drifting toward the same gravitational center. They named this structure Laniakea, which means immense heaven in Hawaiian, a beautifully fitting name for something that spans hundreds of millions of light years. Laniakea isn't a traditional cluster, or even a supercluster in the old sense. It's a gravitational basin, defined not by sharp boundaries but by the flow of galaxies within it. Our own Milky Way sits comfortably within this basin, carried along by currents we're only beginning to understand. The scale of Laniakea challenges our ability to comprehend distance. The local group, our immediate galactic neighborhood, stretches about 10 million light-years across. The nearest major galaxy cluster, the Virgo cluster, lies roughly 50 million light-years away. These distances already strain human imagination, but Laniakea dwarfs them both, extending across roughly 500 million light-years. To put this in perspective, Laniakea contains the equivalent mass of about 100,000 large galaxies, along with vast quantities of dark matter and hot gas floating between them. Light itself, traveling at its incomprehensible speed, would take hundreds of millions of years to cross from one side to the other. Yet even this immense structure doesn't have solid boundaries like the edges of a continent. Instead, its borders are determined by where the flow of galaxies changes direction. Think of watersheds on Earth, those invisible lines that determine whether rainwater flows toward one river system or another. Galaxies within Laniakea drift toward our region, while galaxies just beyond its boundary follow different gravitational currents toward different centers. At the heart of our gravitational basin sits the region we call the Great Attractor, acting as one of the major centers drawing galaxies inward. But it's not alone in shaping these cosmic currents. Beyond it lies an even more massive concentration, called the Shapley supercluster, whose gravitational influence reaches across enormous distances, tugging on galaxies hundreds of millions of light-years away. What makes the concept of Laniakea so remarkable is how it reveals the interconnected nature of cosmic structure. Instead of isolated clusters scattered randomly through space, the universe on large scales resembles a vast network of basins and flows a cosmic landscape sculpted entirely by gravity. This discovery fundamentally changed how we see our place in the cosmos. We're not just residents of a galaxy in a cluster, we're part of a vast river system, flowing along gravitational currents that connect us to structures hundreds of millions of light years away. Every galaxy in our cosmic neighborhood is part of this same great drift, this slow migration toward common gravitational centers. The philosophical implications are profound. We often think of ourselves as isolated, separate from distant parts of the universe. But Laniakea reveals that we're participants in movements that span incredible distances, connected by invisible forces to galaxies we'll never see up close. The same gravity that keeps our feet on the ground connects us to the most distant reaches of our cosmic basin. Mapping the flow of galaxies through space reveals something remarkable about how astronomers detect invisible patterns. Scientists measure galaxy velocities, tracking how fast these cosmic islands move relative to the universe's expansion. When they subtract that expansion component, what remains tells a different story. These peculiar velocities, as researchers call them, show the gravitational tugs and pulls that guide galactic motion. Computer models help trace these movements backward and forward through time, like following breadcrumbs along a cosmic trail. The models identify where galactic flows converge, creating maps that look surprisingly familiar. Streams of galaxies follow filaments through space, flowing into gravitational basins, much the same way rivers merge into lakes, then pour into vast seas. Three-dimensional visualizations of this data revealed something unexpected. The structure wasn't neat or symmetrical, not a tidy sphere or organized cluster. Instead, it formed a sprawling, irregular region shaped by matter's distribution and gravity's patient influence over billions of years. There's something quietly profound about discovering that our galaxy participates in such an enormous, slow dance through space. Human understanding of our cosmic address has shifted dramatically over time. For most of history, people believed the Milky Way was everything, the entire universe contained in that bright band across our night sky. Later discoveries revealed our galaxy as just one among countless billions scattered through space. Now we know even our local supercluster represents only a tiny piece of an incomprehensibly larger gravitational landscape. This revelation might seem unsettling, but many find it oddly comforting instead. We're not drifting alone through dark, empty void. Rather, we belong to structure, part of patterns extending across distances that challenge imagination. The same gravitational laws causing apples to fall and moons to orbit also guide galaxy motion across hundreds of millions of light years. The concept of gravitational basins transforms how we picture cosmic movement. Galaxies aren't rushing toward dramatic collision at some central point. Their motions unfold gently, measured in hundreds of kilometers per second, playing out across billions of years. At such leisurely pace, traveling for all of human civilization's entire history would barely move our galaxy a fraction of the distance toward any cosmic attractor. Beyond these basin boundaries lie other superclusters, each following its own motion patterns. The universe's largest scales resemble vast networks, with filaments and nodes where matter flows along these cosmic highways toward denser regions. Between these crowded filaments stretch enormous voids, regions where galaxies rarely exist. Some voids span hundreds of millions of light years, ranking among the universe's largest known structures. The contrast between dense filaments and empty spaces gives the cosmic web its distinctive character in computer simulations and sky surveys. Images of these structures, often rendered in glowing colors and delicate lines, might appear static, but they're anything but frozen in time. They evolve slowly, changing over billions of years as gravity draws matter into denser concentrations, while universal expansion stretches space itself. These massive structures represent processes rather than fixed objects, snapshots of gravitational flows that have unfolded throughout most of cosmic history. Our understanding remains incomplete, though ongoing observations continue improving, new surveys revealing previously invisible details. Boundaries get refined, roles of various attractors within larger structures evolve with better data. Science frequently works this way, each discovery adding depth to our picture. Sometimes new findings confirm earlier ideas, other times they reshape fundamental concepts. The universe's map isn't a finished document, but an ongoing project, drawn and redrawn as our observational capabilities sharpen. Imagining our position within such vast structures helps to picture standing on a slow-moving ship's deck. The water appears calm, horizon distant, and seemingly unchanging. Yet the vessel drifts steadily with unseen currents. You don't feel the motion directly, but it carries you across enormous distances over time. Our galaxy resembles that ship, carried by gravity's gentle currents through a basin so immense that light requires hundreds of millions of years to cross it. The great Attractor lies somewhere ahead, in this cosmic flow, not as any destination we'll ever reach, but as a region-shaping motion of everything around it. When discussing something so monumentally large, how do we begin grasping its scale? What does it truly mean for structure to span hundreds of millions of light years? How can we translate such measurements into terms the human mind can actually comprehend? The challenge of cosmic scale touches something fundamental about human perception. We evolved understanding distances measured in steps, throws, or at most, horizons. Our brains process cosmic measurements as abstractions, rather than felt experiences. Yet, there's strange beauty in pushing against these limits, in trying to feel our way toward comprehending the incomprehensible vastness that cradles our small, warm world. Imagine standing at the edge of a vast ocean, watching waves roll toward the shore. You can see water stretching to the horizon. You can hear the endless rhythm of the surf, but the true enormity of what lies before you remains somehow beyond your grasp. This is what it feels like when we try to comprehend the scale of superclusters, those immense cosmic structures that dwarf even our wildest attempts at understanding. The human mind evolved to navigate forests and plains, to judge the distance to prey or predator, to estimate how far we might walk before nightfall. We never needed to conceive of distances so vast that numbers themselves begin to lose meaning. Yet here we are, peering into the depths of space, trying to wrap our thoughts around structures so large they make our entire galaxy seem like a grain of sand. For most of human history, the Earth itself represented the ultimate in vastness. A journey of just a few hundred kilometers could take weeks or months to complete. Entire civilizations rose and fell without ever knowing what lay beyond the distant mountains or across the far sea. The horizon marked the edge of the knowable world, and what lay beyond remained forever mysterious. Today, we can cross continents in a matter of hours. The Earth has not shrunk, of course, but our perspective has expanded dramatically. What once seemed impossibly large now feels manageable, almost small. This shift in perspective, this gradual expansion of our mental horizons, lies at the heart of how we come to understand the cosmos. The moon sits about 384,000 kilometers away from us. That distance is so great that light itself, traveling faster than anything else in the universe, needs more than a second to bridge the gap. When you look up at the moon tonight, you are seeing it not as it is now, but as it was a moment ago. This might seem like a trivial delay, but it hints at something profound about the nature of space and time. Sunlight takes roughly 8 minutes to reach our planet. This means that if the sun were to suddenly vanish, we would continue to see it shining in the sky for 8 more minutes before darkness fell. We live our entire lives slightly out of sync with the cosmic events around us, always seeing the past rather than the present. Neptune, the most distant major planet in our solar system, orbits about 4.5 billion kilometers from the sun. Sunlight takes more than 4 hours to reach those frigid outer realms. Already, we have moved far beyond anything we might encounter in our daily experience. These are distances that strain our ability to relate them to familiar things. But our solar system, vast as it seems, occupies only a tiny corner of the Milky Way galaxy. Our galaxy stretches roughly 100,000 light-years from one edge to the other. A light-year represents the distance light travels in a full year, nearly 10 trillion kilometers. When we say the Milky Way spans 100,000 light-years, we are describing something so immense that light itself moving faster than anything else in nature, requires 100,000 years to cross from side to side. Think about that for a moment. Light that began its journey when our ancestors first learned to control fire would only now be reaching the opposite edge of our galaxy. The entire history of human civilization, from the first stone tools to space exploration, represents just a brief flicker in the time it takes light to traverse our cosmic neighborhood. And yet, the Milky Way is just one galaxy among hundreds of billions scattered throughout the observable universe. The nearest large galaxy to our own, Andromeda, lies approximately 2.5 million light-years away. When you look at Andromeda through a telescope, you are seeing light that began its journey long before humans existed in anything resembling their modern form. You are literally looking back through time, witnessing the ancient past of a distant world. The space between galaxies appears mostly empty to our eyes, but gravity weaves invisible threads that link these island universes together. Our local group of galaxies, which includes the Milky Way, Andromeda, and dozens of smaller companions, spans roughly 10 million light-years. This represents a distance so vast that light crossing it today began its journey before complex life had even emerged on Earth. But even our local group represents only a small piece of a much larger puzzle. Gravity organizes galaxies into clusters, and clusters into superclusters, creating a hierarchy of structure that extends across hundreds of millions of light-years. The Virgo cluster, one of the dominant structures in our cosmic neighborhood, contains thousands of galaxies and spans tens of millions of light-years. Beyond Virgo lies an even grander arrangement, a supercluster that encompasses our local group, Virgo itself, and countless other clusters and groups of galaxies. These superclusters represent some of the largest structures in the known universe, extending across distances that challenge our very ability to conceive of space and time. What does it really mean to say that a supercluster spans hundreds of millions of light-years? Numbers alone cannot convey the true scale of such distances. Perhaps it helps to think in terms of time, the most fundamental measure of human experience. If a beam of light began its journey at one edge of a supercluster when the first dinosaurs were just beginning to appear on Earth, that light might only now be reaching the opposite side. Consider what this means. The entire age of dinosaurs, spanning over 160 million years, the catastrophic extinction that ended their reign, the rise of mammals, the emergence of our own species, the development of language, the invention of agriculture, the building of cities, the birth of science and technology, all of human history from the first cave paintings to space telescopes, all of it would unfold in the time required for light to cross a single supercluster. We might also think about motion to grasp these scales. Galaxies hurtle through space at speeds of hundreds, or even thousands of kilometers per second. By any ordinary measure, these represent almost incomprehensible velocities. Yet even at such tremendous speeds, crossing a supercluster would require billions of years, a significant fraction of the age of the universe itself. This is why superclusters cannot be tightly bound structures in the same way that galaxies or smaller galaxy clusters are held together. Their gravity influences the motion of galaxies within them, guiding vast flows of matter across cosmic time. But the expansion of the universe itself also plays a role, gradually stretching space on these larger scales. Some parts of a supercluster may remain gravitationally connected, while others slowly drift apart over billions of years. When astronomers first began mapping these enormous structures, they discovered something remarkable. Superclusters do not exist in isolation, scattered randomly through space. Instead, they connect to one another through filaments of galaxies, creating a vast web-like structure that spans the observable universe. Between these filaments lie immense voids, regions of space that contain almost no galaxies at all. The universe on its largest scales resembles a cosmic sponge, with matter concentrated along thin strands and enormous empty regions in between. This cosmic web provides the framework within which structures like superclusters form and evolve. It represents the largest scale organization of matter that we can observe, a pattern that emerged from tiny quantum fluctuations in the very early universe. In this grand cosmic web, Galaxies move like traffic on highways of dark matter, flowing along the filaments toward the densest regions where superclusters form. The journey takes billions of years, playing out over timescales that dwarf human comprehension. We are witnessing a slow-motion dance of cosmic architecture, a ballet of gravity and expansion that has been unfolding since the universe was young. Galaxies don't exist in isolation, floating alone through the cosmic void. They're part of something much grander, an interconnected web that gravity has been weaving for billions of years. When we try to wrap our minds around these distances, we run into a fundamental problem. Our brains evolved to understand the world around us, where we measure things in steps and car rides, where time passes in heartbeats and seasons. The human mind simply wasn't built to comprehend millions of light years. It's like asking your eyes to see radio waves, or your ears to hear colors. Astronomers know this struggle well, so they've become masters of comparison and analogy. Picture the Milky Way shrunk down to the size of your dinner plate. On that same scale, our entire solar system becomes smaller than a single grain of sand. The nearest star to us would sit several meters away from that grain of sand. Dial's eyes to sit several meters away from that grain of sand. Now imagine that dinner plate is just one of many, scattered across an entire continent. That's how galaxies are spaced within a supercluster. The comparison still falls short, but it gives our mind something to grab onto. Here's another way to think about it. If we could shrink the entire observable universe down to the size of Earth, a supercluster would still be as large as a major country. The Milky Way would become a small city within that country. Our solar system would shrink to the size of a single building, and Earth itself would become microscopic. These analogies aren't perfect, they can't be, but they serve as anchors for our imagination. Familiar handholds as we climb toward understanding something fundamentally unfamiliar. There's another dimension to this scale that often gets overlooked, and that's mass. Superclusters don't just contain vast numbers of galaxies, they're also home to enormous quantities of dark matter, which outweighs all the visible matter by several times over. This invisible substance forms halos and filaments throughout space, acting like cosmic scaffolding that guides the motion of galaxies along gravitational pathways. The total mass of a supercluster can reach millions of billions of times the mass of our Sun. These numbers quickly become meaningless to us, but they point to something profound about the nature of gravity itself. Gravity is actually the weakest of the four fundamental forces when you're dealing with small scales. But when enormous amounts of matter come together, gravity becomes the dominant player. It's gravity that gives superclusters their structure, pulling matter into vast filaments and clusters, orchestrating the slow dance of galaxies across hundreds of millions of light years. Yet even gravity has its boundaries. On the very largest scales, something else takes over. The expansion of the universe, driven by the mysterious force we call dark energy, gradually overcomes gravitational attraction. This causes the most distant structures to recede from one another, like cities drifting apart as the continent beneath them grows larger. This ongoing tension between gravity, trying to pull things together, and expansion trying to push them apart, adds another layer to our understanding of cosmic scale. Superclusters aren't permanent monuments in space. Over billions of years, their shapes and boundaries slowly change. Some regions become more tightly bound as gravity wins local battles, while others drift apart, carried by the expansion of space itself. There's something almost meditative in that thought. Even the largest structures in the universe are part of an ongoing process, evolving slowly over cosmic time. It's a reminder that permanence, as we understand it, is largely an illusion created by our brief perspective on time. When we ask how big superclusters really are, the answer becomes surprisingly complex. If we define them by where we see galaxies clustered together, their sizes vary wildly, from tens of millions to hundreds of millions of light years across. If we define them by gravitational flows, by tracking how galaxies actually move through space, their boundaries become even more complex, shaped by motion rather than simple geometry. Either way, the scale remains immense beyond ordinary comprehension. Understanding that scale matters, though, because it provides the framework for everything else we study about the universe. The way galaxies move, how clusters form, where dark matter concentrates, and how mysterious attractors influence vast regions of space. All of this makes more sense when we see it within the enormous framework of superclusters. Sometimes there's something oddly comforting about contemplating these immense scales. Our daily concerns feel immediate and urgent, measured in deadlines and appointments. But galaxies drift for billions of years. Light travels for millions of years just to reach our telescopes. Structures hundreds of millions of light years across evolve at a pace so gradual it's almost timeless. This perspective shift can be profound. The universe reveals itself as vast but patient. Change happens but slowly. Motion occurs but gently. Even the largest flows of galaxies resemble the steady movement of tides rather than the rush of rapids. There's a cosmic rhythm here that operates on scales we can barely imagine. The dark matter that shapes these structures remains one of the great mysteries of our time. We can see its effects, the way it bends light and influences the motion of visible matter, but we still don't know what it actually is. It's like trying to understand a symphony by feeling the vibrations in the floor, knowing something magnificent is happening, but unable to hear the music directly. This invisible scaffolding of dark matter creates highways through space, channels along which galaxies flow over cosmic time. These aren't roads in any sense we'd recognize, but rather subtle gravitational gradients that guide the motion of entire stellar cities across distances that dwarf air and air. The universe we observe today, with its intricate web of galaxies and vast cosmic structures, began from something almost impossibly simple. Picture the earliest cosmos as a nearly perfect expanse, smooth and uniform in ways that seem almost too orderly to be real. This primordial state was hot, dense, and filled with matter, distributed so evenly that if you could somehow peer across its vastness, you would find little to distinguish one region from another. Within this apparent perfection, however, lay the seeds of everything we see today. Tiny fluctuations in density, so small they represented just 1 part in 100,000, existed like whispers in an otherwise silent room. These variations were invisible, imperceptible to any observer, yet they carried within them the blueprint for billions of galaxies, countless stars, and the very fabric of cosmic architecture. The force responsible for transforming these minute differences into the grand structures we observe is gravity, operating with a patience that spans eons. Gravity possesses a quality that sets it apart from other forces in nature. It never truly cancels itself out, and it accumulates relentlessly. When you sit in a chair, you don't feel pulled toward the table across the room, and furniture doesn't visibly attract other furniture. Yet gravity's influence extends infinitely, always adding up, always building upon itself. In those early epochs, regions with even slightly more matter than their surroundings began to exert a marginally stronger gravitational pull. This tiny advantage allowed them to draw in additional material from nearby areas. As more matter accumulated, the gravitational attraction grew stronger still, creating a cycle that would continue for billions of years. Scientists call this process gravitational instability, and it represents the fundamental mechanism through which the universe builds complexity from simplicity. Think of this process like water collecting on a nearly flat surface after a gentle rain. Initially, the water spreads evenly across the ground. Small depressions, barely noticeable at first, begin to gather slightly more water than the areas around them. As these shallow pools fill, they become deeper, attracting even more water from their surroundings. Gradually, what started as minor variations transform into puddles, streams, and eventually larger bodies of water. The universal's a similar pattern, with gravity serving as the invisible slope that guides this cosmic flow. Central to this story is an ingredient that remains largely mysterious: dark matter. The atoms that compose stars, planets, and our own bodies represent only a small portion of the universe's total mass. Dark matter, which outweighs ordinary matter by several times, interacts primarily through gravitational attraction. It neither emits nor absorbs light, making it invisible to direct observation. Yet, its presence reveals itself through the rotation of galaxies, the motion of galaxy clusters, and the way light bends as it travels through space. Dark matter began clustering together very early in cosmic history, forming the first gravitational wells that would later become the scaffolding for visible structures. Hot gas composed of ordinary matter gradually fell into these invisible wells, cooling and condensing over time until conditions became right for the first stars to ignite. Without dark matter's early influence, this entire process would have unfolded far more slowly, and the universe might have developed a completely different architectural pattern. As galaxies emerged from this primordial soup, they didn't remain solitary islands, scattered through space. Gravity continued its patient work, drawing individual galaxies together into groups and clusters. Over hundreds of millions of years, these clusters themselves began to organize into even larger associations, connected by vast filaments of dark matter and gas threading through the cosmos. This gave rise to what astronomers call the cosmic web, a structure so vast it spans the entire observable universe. Imagine a three-dimensional spiderweb stretched across billions of light years, with galaxies strung like dewdrops along its filaments, and enormous empty regions called voids occupying the spaces between. Computer simulations have proven invaluable for understanding how this grand architecture developed. Scientists can recreate the conditions present in the early universe and allow virtual gravity to act over simulated billions of years. In these digital universes, tiny fluctuations gradually evolve into filaments, dense nodes, and empty voids, creating patterns that mirror what telescopes reveal in the real cosmos. There's something almost meditative about watching these simulations unfold. Matter flows along invisible highways, slowly congregating into increasingly complex structures. Nothing happens rapidly. Everything operates on timescales that dwarf human experience. Galaxies drift through space, occasionally merging with their neighbors, reshaping themselves through processes that unfold over billions of years. This cosmic evolution continues today, though at a pace so gradual that it appears frozen from our brief human perspective. Galaxy clusters still grow through the addition of new members. Filaments of dark matter continue to channel material toward dense regions, and the overall web-like structure slowly becomes more pronounced. The same gravitational instability that created the first slight concentrations of matter billions of years ago still operates throughout the universe, building ever more complex arrangements from the simple attraction between masses. The cosmic web represents more than just the current distribution of matter in space. It tells the story of how complexity emerges from simplicity, how tiny imperfections in an otherwise uniform beginning can grow into the rich, structured universe we inhabit. Every galaxy, every star, every planet exists because of those minute density variations present shortly after the beginning of time, amplified through eons of gravitational attraction into the magnificent cosmic architecture that surrounds us. The universe builds itself like a patient architect, starting small and working its way up to something magnificent. Picture this process unfolding over billions of years, where the tiniest pieces come together first, then gradually combine into ever larger structures. It's a bit like watching a city grow from scattered houses into neighborhoods, then districts, and finally into sprawling metropolitan areas. Stars are born within the cradles of galaxies, these island universes spinning quietly in space. But galaxies themselves don't stay isolated for long. They drift toward each other, pulled by invisible threads of attraction, gathering into small groups. These groups eventually merge and combine, forming massive clusters that contain thousands of galaxies. And even these clusters don't mark the end of the story. They link together across unimaginable distances, creating what we call superclusters, some of the largest organized structures that exist anywhere. What drives this cosmic construction project is gravity, but not the kind of gravity you feel when you drop your keys. The gravity operating on these scales works nothing like what we experience day to day. Here on Earth, gravity acts quickly and obviously, pulling everything straight down toward the ground beneath our feet. But out in the depths of space, gravity becomes something entirely different, something almost philosophical in its patience. Across the vast emptiness between galaxies, gravity works its influence over distances so enormous that light itself takes millions or billions of years to cross them. The effects unfold with a slowness that defies human comprehension. Galaxies respond to gravitational pulls that originated when the universe was young, drifting through space in response to tugs they've been feeling for longer than complex life has existed on Earth. This cosmic choreography plays out against the backdrop of an expanding universe, creating a fascinating tension between opposing forces. While gravity works tirelessly to pull matter together, the expansion of space itself pushes distant regions apart. It's like trying to build a sandcastle while the beach slowly stretches beneath your hands. The outcome of this cosmic tug-of-war depends entirely on which force wins in any given region. Where gravity proves stronger, matter collapses inward, forming the dense filaments and clusters that light up our telescopes with the glow of billions of stars. But where expansion dominates, something remarkable happens instead. Matter spreads out, becoming so dilute that vast regions contain almost nothing at all. These empty regions, called cosmic voids, represent some of the most extraordinary structures in the universe. Imagine bubbles of near-perfect emptiness, each one spanning hundreds of millions of light-years from edge to edge. They're so large that you could fit thousands of galaxies end to end, across their width, yet they contain almost nothing. The contrast is striking. Dense threads of galaxies surrounding these enormous bubbles of nothingness, creating what astronomers call the cosmic web. As structures grow larger and more massive, their gravitational influence extends ever farther into space. The most massive galaxy clusters create gravitational fields so powerful they can influence the motion of galaxies across distances that boggle the mind. This is how features like the Great Attractor emerge, not as isolated objects sitting alone in space, but as part of a larger gravitational landscape that shapes the motion of matter across significant portions of the observable universe. Perhaps most remarkably, this entire process continues even now, unfolding around us as we speak. Galaxies merge with their neighbors, clusters grow more massive as they capture wandering galaxies, and matter continues its slow journey along the filaments of the cosmic web. The universe remains very much a work in progress, a dynamic system that will look different tomorrow than it does today, though the changes occur so slowly that countless human generations might pass without anyone noticing. If you could somehow position yourself far above this cosmic web and watch it evolve in fast forward, like a time-lapse video spanning billions of years, the sight would be breathtaking. Filaments would brighten as galaxies gather along them like beads on invisible strings. Clusters would swell as they merge with their neighbors, while voids expand like bubbles rising through cosmic foam. The motion would appear almost organic, like watching a vast living system grow and change. There's something deeply comforting about the steadiness of it all. Gravity doesn't rush its work or act in sudden dramatic bursts. Instead, it operates with infinite patience, drawing matter together over time, spans that dwarf human history. Even the largest structures we can observe formed through countless small steps, each one guided by the same fundamental law that makes apples fall from trees. This gradual accumulation and flow explains how superclusters and other massive structures come to exist. They don't spring into being during dramatic cosmic events. Instead, they emerge from the collective motion of countless galaxies, each one responding to gravitational influences from its surroundings, like dancers in an incredibly slow and complex ballet. But gravity alone doesn't control the entire story. On the largest scales imaginable, another force enters the picture, one that works in the opposite direction entirely. Dark energy, perhaps the most mysterious phenomenon in all of physics, drives the accelerated expansion of space itself. This expansion gradually stretches the fabric of the universe, making it progressively harder for gravity to pull distant structures together. Over the coming billions of years, this expansion will win out over gravity. On the largest scales, isolating galaxy clusters and superclusters from each other. They'll drift apart like islands in an ever-expanding ocean, separated by distances that grow larger with each passing moment. Eventually, these structures will become so isolated that they'll lose all contact with each other, each one becoming a separate universe unto itself. This ongoing battle between gravity and expansion shapes not only where matter gathers in the universe, but also how long those gatherings can remain connected. When astronomers observe massive structures like the Great Attractor and map the flows of galaxies responding to its pull, they're capturing just one moment in this vast ongoing process. The universe we see today represents a snapshot of structures still forming, still changing, still responding to the slow dance between forces that want to bring things together and forces that want to push them apart. It's a reminder that even on the largest scales, nothing remains static. Everything flows, everything changes, everything evolves according to laws that operate with a patience that spans cosmic time. Behind much of this cosmic architecture lurks dark matter, the invisible scaffolding that outweighs everything we can see by a factor of 5 to 1. This hidden mass provides much of the gravitational pull that guides the formation of structures and drives the vast flows of galaxies across space. Without dark matter, the universe would look completely different, perhaps remaining largely smooth and featureless instead of developing the rich tapestry of structures we observe today. Imagine looking down at the universe from some impossible vantage point, watching galaxies the way you might watch cars from a skyscraper window. You'd notice something puzzling right away. These cosmic islands of stars are spinning faster than they should, moving in ways that visible matter alone simply cannot explain. The stars we see, the glowing gas clouds, all the bright spectacular things that fill our telescopes, they're not heavy enough to account for what's actually happening out there. It's like watching a carousel spin at full speed when you can only see enough machinery to power a gentle rotation. This mystery deepens when you zoom out even further. Galaxy clusters, these massive neighborhoods containing hundreds or thousands of galaxies, are held together by gravity. But when astronomers measure how fast these galaxies are racing around within their clusters, the numbers don't add up. The visible matter provides nowhere near enough gravitational pull to keep everything bound together. These clusters should be flying apart, scattering their galaxies across space like marbles from a broken bag. Yet there they are, stable, persistent, as if something invisible is acting like cosmic glue. The evidence for this invisible presence shows up in the most elegant ways. Light itself becomes a detective tool. When light from distant galaxies passes through massive galaxy clusters, it bends and warps according to Einstein's predictions about gravity and spacetime. The amount of bending tells us how much mass is doing the warping. Time after time, these measurements reveal far more mass than we can actually see. It's as if the universe is full of invisible architects, shaping the paths of light and matter with their gravitational influence. Scientists call this hidden component dark matter, though the name is almost misleadingly simple. This isn't matter that's merely dim or hard to spot. This is matter that doesn't interact with light at all. It doesn't shine, doesn't glow, doesn't absorb or reflect electromagnetic radiation in any detectable way. Yet it's everywhere, and it's abundant. Current estimates suggest that dark matter outweighs all the visible matter in the universe by about 5 to 1. Everything we can see, every star, planet, and glowing nebula, represents only about 20% of all the matter that exists. The story of how we discovered this cosmic mystery begins with individual galaxies and their rotation patterns. In the early 20th century, astronomers started measuring how fast stars orbit around galactic centers. Basic physics suggested a simple pattern. Stars closer to the center should move faster, stars farther out should move slower, just like planets in our solar system. But that's not what observers found. Stars in the outer reaches of spiral galaxies were moving just as fast as stars near the core. The rotation curves were flat, defying gravitational expectations. This implied that galaxies contain much more mass than meets the eye, distributed in vast halos extending far beyond the visible disk. The pattern repeated itself on larger scales. Galaxy clusters revealed the same discrepancy between visible mass and gravitational behavior. The galaxies within clusters were moving too fast to be held together by visible matter alone. Something unseen was providing the additional gravitational binding. Computer simulations help us understand how profound this influence really is. When scientists model the evolution of the universe, including dark matter, they see structures forming that match real observations beautifully. Vast cosmic webs of filaments and nodes emerge, with galaxies lighting up like cities along invisible highways. Remove dark matter from these simulations, and the universe becomes a much emptier, smoother place. The rich tapestry of galactic clusters and superclusters that we observe simply doesn't form without this invisible scaffolding. This scaffolding began its work very early in cosmic history. In the first few 100,000 years after the Big Bang, ordinary matter was essentially trapped by intense radiation pressure. It couldn't clump together effectively because photons kept pushing it around. Dark matter, however, remained immune to this interference. It began forming gravitational wells long before ordinary matter could settle down. When the universe finally cooled enough for atoms to form and radiation pressure to ease, ordinary matter fell into these pre-existing dark matter structures. In this sense, every galaxy, every star, every planet owes its existence to dark matter's early architectural work. The visible universe arose within a framework that had been quietly organizing itself in the cosmic darkness. This invisible influence extends to the largest motions we can observe. Vast streams of galaxies flow through space, as if following predetermined paths. These motions hint at massive gravitational attractors, regions where dark matter has concentrated in amounts that dwarf even the largest galaxy clusters. The paths these galactic flows follow make sense only when we account for dark matter's distribution. It's like watching leaves float downstream and inferring the shape of an invisible riverbed from their trajectories. Despite decades of evidence for its existence, dark matter's true nature remains one of physics' greatest puzzles. We know it's there because of what it does, but we don't know what it is. It doesn't appear to be made of atoms or any particles we've encountered in laboratories. The leading candidates are exotic particles that interact with ordinary matter only through gravity. These hypothetical particles would pass through normal matter almost as if it weren't there, occasionally colliding with atomic nuclei in interactions so rare they require incredibly sensitive detectors to spot. Underground laboratories around the world house these detectors, shielded from cosmic rays and other interference that might create false signals. Scientists wait and watch for the telltale signs of dark matter particles, revealing themselves through the faintest possible interactions. So far, these experiments have yielded tantalizing hints, but no definitive detections. Dark matter continues to interact with our universe primarily through its gravitational signature, shaping cosmic structure while remaining directly invisible to our instruments. There's something almost philosophical about this cosmic hide and seek. The universe appears to be largely composed of something we cannot see, touch, or directly detect. Most of reality operates beyond the reach of our senses and instruments, known to us only through its effects on the small fraction of matter that does interact with light. It reminds us how much of existence might be playing out in dimensions or through mechanisms we haven't yet learnt to perceive. The visible universe, spectacular as it is, may be just the bright trim on a vast cosmic tapestry woven primarily from invisible threads. The cosmos holds secrets that dwarf our everyday understanding of what exists. Most of the universe, around 95% of it, remains completely invisible to our eyes and instruments. This isn't some distant philosophical concept. It's the fundamental reality we live within. Every star you see at night, every galaxy captured in telescopic images, represents just the tiny visible portion of something vastly larger. Dark matter doesn't announce itself with light or heat. It simply exists, exerting its gravitational influence across billions of years. Think of it like the foundation of a house, completely hidden beneath the floorboards, yet supporting everything you can actually see. Without this invisible framework, galaxies would fly apart, unable to hold their spiral arms together as they spin through space. The cosmic microwave background, that faint radiation left over from the universe's infancy, tells us remarkable things about this hidden reality. When scientists analyze the tiny temperature variations in this ancient light, They're essentially looking at baby pictures of the universe. These fluctuations reveal how matter was distributed when everything was only a few 100,000 years old. The patterns show us that ordinary matter, the stuff that makes planets and people, accounts for merely 5% of everything that exists. 25% consists of dark matter, that invisible scaffolding we've been discussing. The remaining 70% is something even stranger, dark energy, which pushes the universe apart at an accelerating rate. So when we observe the movement of galaxies toward massive structures like the Great Attractor, we're witnessing the influence of this predominantly invisible cosmos. Gravity operates like a patient sculptor, working on timescales that make human history seem like a brief moment. The forces moving entire galaxies don't rush or surge. They pull steadily across millions of centuries. Our own Milky Way participates in this cosmic dance, drifting along with thousands of other galaxies through what astronomers call the Laniakea supercluster. The Great Attractor itself demonstrates how misleading our visible universe can be. What appears to be pulling galaxies toward a specific region isn't really a single massive object. Instead, it's the combined gravitational effect of enormous amounts of matter, most of it completely dark, spread across vast filaments and halos that extend far beyond anything we can directly observe. These dark matter structures form the backbone of cosmic architecture. Visible galaxies mark where this invisible material has concentrated most densely, like light strung along an otherwise invisible web. The galaxies themselves are merely the bright decorations on a framework we cannot see. Galaxy clusters move through space in large-scale flows, following gravitational currents established by this hidden mass distribution. The motion resembles water flowing through underground channels, guided by topography we cannot directly map. Scientists can only infer the shape of this dark landscape by observing how visible matter moves within it. The cosmic web, as astronomers call this structure, consists of filaments, walls, and vast empty regions called voids. Dark matter forms the primary component of this web, with ordinary matter following its gravitational lead. Where dark matter concentrates, galaxies form. Where it remains sparse, we find cosmic deserts nearly empty of stars. Computer simulations of cosmic evolution reveal how this invisible architecture develops over time. Starting from tiny fluctuations in the early universe, dark matter gradually clumps together under its own gravity. These growing concentrations eventually become massive enough to trap ordinary matter, which then forms the first stars and galaxies. The relationship between visible and invisible matter creates a kind of cosmic irony. Everything we can observe, from the smallest planet to the largest galaxy cluster, represents just the foam on an ocean of darkness. Yet this darkness isn't empty or lifeless. It's the very foundation that makes visible structures possible. Understanding dark matter requires accepting that reality extends far beyond human perception. Our senses evolved to navigate a world of solid objects and visible light, not to comprehend the invisible forces shaping the cosmos. Yet through careful observation and mathematical analysis, we can map this hidden realm with surprising precision. The Great Attractor region contains not just the galaxies we can see, but massive halos of dark matter extending in all directions. These halos can stretch for millions of light years, creating gravitational fields that influence galaxy motion across enormous distances. The visible galaxies are like islands in a vast dark sea, their positions and movements determined by currents they cannot control. This invisible majority of the universe operates according to the same physical laws that govern visible matter, yet it interacts with ordinary matter almost exclusively through gravity. Dark matter particles, whatever they might be, don't emit light, don't absorb light, and don't collide with each other in the ways that normal atoms do. Scientists continue searching for direct evidence of dark matter particles, building increasingly sensitive detectors deep underground, shielded from cosmic rays and other interference. The hunt for these elusive particles represents one of the greatest mysteries in modern physics, a puzzle that could reshape our understanding of reality itself. Meanwhile, the cosmic flows continue their patient journey through space, carrying our galaxy along with countless others toward regions of higher mass concentration. The Great Attractor may itself be just one part of an even larger structure, a single feature in a gravitational landscape that extends across hundreds of millions of light years. The cosmos operates on scales that challenge our everyday understanding of what attracts what. When scientists first spoke of something called the Great Attractor, our minds naturally pictured a single, massive object, something like an enormous galactic cluster, sitting in one spot, pulling everything toward it like a cosmic magnet. But the universe rarely offers such simple explanations. As telescopes improved and measurements became more precise, this neat picture started to unravel. What emerged was something far more intricate and perhaps more beautiful in its complexity. The Great Attractor wasn't discovered by spotting a bright, obvious structure in space. Instead, astronomers noticed something peculiar about how galaxies move. Streams of galaxies, including our own, were drifting in the same general direction. This collective motion pointed somewhere, but not to a precise point, more like toward a broad region of space. Think of walking through a valley on a foggy morning. You feel cool air flowing downhill, you see water moving in streams, all heading the same way. But with the mist hiding the landscape, you can't tell if there's one deep basin ahead, or maybe several hills and valleys guiding the flow. The motion tells you something about the shape of the land, but the fog keeps the full picture hidden. Astronomers found themselves in exactly this situation. Galaxy motions revealed a gravitational slope, but the exact structure creating that slope remained mysterious. Part of the challenge came from what scientists call the zone of avoidance. This is the region of sky blocked by our own galaxy's dust and stars. When better instruments finally pierced through this cosmic fog, they revealed the Norma cluster. This structure contains hundreds of large galaxies, along with vast amounts of hot gas and dark matter. For a while, it seemed like this might be the Great Attractor itself, but the math didn't quite work out. The gravitational influence affecting nearby galaxies seemed stronger than what the Norma cluster alone could provide. This led to a fundamental shift in thinking. Rather than being one object, the Great Attractor might be more like a neighborhood, a region where multiple structures create a combined gravitational pull. Imagine the difference between a single mountain peak and an entire mountain range. Both can guide the flow of rivers and weather patterns, but the mountain range affects a much broader area through the combined influence of many peaks and valleys. Gravity works this way too. You don't need one supermassive object to create large-scale motion. A broad distribution of mass, spread across hundreds of millions of light-years, can shape the movement of entire regions of space. Multiple clusters, groups of galaxies, and invisible filaments of dark matter all contribute their gravitational influence. As galaxy surveys expanded beyond the immediate neighborhood, astronomers discovered something even more intriguing. The flow of galaxies doesn't stop at the Great Attractor. It continues farther out, toward even larger concentrations of matter. One of these distant structures is the Shapley supercluster, located several hundred million light-years beyond the Great Attractor. This collection of galaxy clusters ranks among the most massive structures in the nearby universe. It contains dozens of rich clusters and enormous amounts of dark matter, and its gravitational reach extends across vast distances. Many scientists now think that part of what we attributed to the Great Attractor actually comes from this much more distant structure. It's like discovering that the river you thought was flowing toward a nearby lake is actually part of a much larger watershed, ultimately draining toward an ocean hundreds of miles away. This doesn't make the Great Attractor any less real or important. It just means we're seeing one part of a much grander gravitational landscape. Rivers provide a good analogy here. Water might flow toward a lake, but that lake might drain into a larger river, which feeds into an even larger basin downstream. The motion of water reflects the entire shape of the continent, not just one geographic feature. Galaxies move along gravitational slopes, shaped by multiple structures, some closer, some farther away, all contributing to the overall pattern of cosmic motion. The Great Attractor represents one significant slope in this vast topography of space. Scientists think about these patterns in terms of gravitational basins. A basin isn't defined by sharp boundaries, but by the flow of matter within it. Galaxies inside a basin drift toward a common region, while galaxies outside flow in different directions. The Great Attractor sits within such a basin, acting as a major center of gravitational convergence. But it's not necessarily the final destination of cosmic flow, nor the only source of gravitational influence in the region. Modern astronomical surveys can trace galaxy movements across hundreds of millions of light-years, creating maps that show streams of galaxies converging toward high-density regions. These patterns look remarkably like river systems, with smaller streams feeding into larger ones, ultimately flowing toward the biggest basins. Computer simulations add another layer of understanding. When scientists model how structure grows in the universe, including the effects of dark matter and dark energy, they find that mass naturally accumulates in extended regions rather than isolated points. Clusters form along filaments of dark matter. These filaments intersect to create superclusters. Together, these structures form a vast network of gravitational influences. In such a network, the concept of one dominant object becomes almost meaningless. What matters is how mass distributes itself across enormous volumes of space. The Great Attractor emerges as a particularly dense node in this cosmic web, one of several regions shaping galactic motion in our corner of the universe. Time adds yet another dimension to consider. The structures we observe today have been growing and evolving for billions of years. Dark matter began clumping together when the universe was much younger and smaller. Over cosmic time, these clumps grew larger and more complex, eventually forming the network of filaments and nodes we see today. The motion we observe reflects this deep history. Galaxies aren't just responding to current gravitational influences, they're following paths carved out by billions of years of cosmic evolution. The Great Attractor represents both a destination and a waypoint, a place where matter has been gathering since the early universe began organizing itself into the large-scale structure we observe today. This perspective transforms our understanding of cosmic motion from something simple and direct into something more like a vast, slow dance. Galaxies move not toward single destinations, but along currents shaped by the combined mass of countless structures, all pulling and flowing according to gravity's patient choreography across space and time. The universe we inhabit is far from still. On scales that stretch our imagination, massive structures shift and flow through space like rivers of starlight. These cosmic currents carry entire galaxies along their paths, including our own Milky Way swept up in motions that began billions of years ago. When we try to understand what drives these vast movements, we quickly discover that the answer isn't simple. Gravity shapes the cosmos like an invisible hand, pulling matter toward regions where it has already gathered. The denser an area becomes, the stronger its pull grows, creating what astronomers call gravitational wells. These wells act like cosmic valleys, drawing in everything around them. Picture a landscape, carved by flowing water. Small streams merge into larger ones, which eventually join mighty rivers flowing toward the sea. The universe operates on similar principles, but instead of water, it's galaxies that flow along channels carved by gravity itself. These cosmic streams stretch across distances so immense that light takes hundreds of millions of years to cross them. Our local region of space participates in one such flow. Measurements reveal that galaxies throughout our cosmic neighborhood drift in a particular direction, as if pulled by some enormous unseen mass. This discovery puzzled astronomers for decades. What could be massive enough to influence such a vast region of space? The search for answers led to the identification of what became known as the Great Attractor. This mysterious gravitational influence seemed to explain why galaxies in our area of the universe all share a common drift. Yet the more scientists studied this phenomenon, the more complex the picture became. Initially, researchers imagined the Great Attractor as a single, massive object hidden behind the dust and stars of our own galaxy. Like a traveler spotting a distant hill, they could detect its influence without seeing it directly. But as technology improved and observations became more detailed, this simple picture gave way to something far more intricate. The Great Attractor isn't really a single thing at all. Instead, it's a region where multiple galaxy clusters have gathered, creating a gravitational landscape filled with peaks and valleys. Dense clusters like Norma and Centaurus contribute to this cosmic terrain, each adding their mass to the overall pull that affects our galactic neighborhood. This revelation mirrors how our understanding often evolves. We start with simple explanations that help organize what we observe. A mysterious force becomes a hidden object, which eventually reveals itself as a complex system of interacting parts. Each new layer of understanding brings us closer to grasping the true nature of what we're studying. But the story doesn't end there. As astronomers mapped galaxy motions with greater precision, they realized that even the Great Attractor couldn't fully explain the flows they observed. Something else, something even more massive, seemed to be pulling from beyond. Think of following a river upstream. You might assume the nearby lake is the source of all that flowing water. But if you keep exploring, you discover that the lake itself is fed by an even larger river, which eventually leads to distant mountains, where the real source lies hidden among peaks and valleys. The cosmic equivalent of those distant mountains is a structure called the Shapley concentration. Located roughly twice as far from us as the Great Attractor region, this enormous gathering of matter contains dozens of galaxy clusters packed into a relatively small volume of space. Even by cosmic standards, it's exceptionally dense and massive. The Shapley concentration lies between 600 and 700 million light-years from Earth. To put this distance in perspective, light that left those galaxies when complex life was just beginning to flourish on our planet is only now reaching our telescopes. Yet despite this vast separation, the gravitational influence of Shapley reaches across the intervening space to affect the motion of galaxies in our region. What makes Shapley particularly remarkable is its concentrated nature. Many cosmic structures spread their mass across enormous volumes, like cities sprawling across vast metropolitan areas. Shapley, by contrast, packs its matter into a relatively compact core, creating one of the deepest gravitational wells in our cosmic neighborhood. This concentration of mass helps explain why galaxy flows appear stronger than nearby structures alone could account for. The motion we observe isn't caused by a single gravitational source, but by the combined influence of multiple regions, each contributing its pull to the overall pattern that carries galaxies through space. Understanding this layered influence requires thinking about gravity in a new way. Rather than imagining it as a simple tug from one direction, picture it as a gentle slope, shaped by many features. A nearby hill might dominate your immediate surroundings, but distant mountain ranges still influence the overall shape of the terrain you're standing on. The Great Attractor represents one significant feature in this gravitational landscape, while Shapley forms part of an even larger rise beyond it. Together, they create the cosmic geography that guides the flow of galaxies across hundreds of millions of light-years. This understanding reveals something profound about the nature of cosmic structure. The universe organizes itself into a vast web of matter and empty space, with filaments of galaxies connecting dense nodes where clusters gather. These nodes act like cities in the cosmic web, concentrating mass and creating the gravitational influences that shape large-scale motions. None of these structures remain static over time. Cosmic evolution ensures that clusters merge, filaments shift, and gravitational influences change as matter continues to flow along the web's pathways. The Great Attractor itself will likely evolve, eventually becoming part of even larger structures as the universe ages. This constant change reminds us that the universe is dynamic on every scale. The motions we measure today are snapshots of an ongoing process that began with tiny fluctuations in the early cosmos and continues to unfold across billions of years. What we see is just one moment in a story that started long before Earth formed and will continue long after our sun burns out. There's something both humbling and comforting about this gradual revelation of cosmic structure. The universe doesn't reveal all its secrets at once. Instead, it invites us to look more carefully, measure more precisely, and think more deeply about what we discover. Each new observation rewards our patience with deeper understanding. When we ask whether the Great Attractor is a single object or something more complex, we find that it's both less and more than we initially imagined. Less because it isn't a solitary giant dominating its surroundings, more because it's part of an immense network of mass and motion, extending far beyond what early astronomers could have conceived. This progression, from simple to complex understanding, is typical of how science advances. Early discoveries provide names and concepts that help us organize our observations. As more data becomes available, those concepts become more nuanced, revealing deeper layers of structure and connection that were always there, waiting to be discovered. The story of the Great Attractor and Shapley concentration illustrates something fundamental about cosmic architecture. On the largest scales, the universe resembles a vast city, with neighborhoods of varying density connected by highways of flowing matter. We happen to live in one such neighborhood, carried along by currents that stretch across distances almost too large to comprehend. In the early 1900s, an astronomer named Harlow Shapley was busy studying something called globular clusters. These are tight groups of stars that orbit around our galaxy, the Milky Way. Shapley was trying to figure out how big our galaxy really was and where our sun sat within it. He had no idea that decades later, astronomers would discover a massive cosmic structure and name it after him. The Shapley concentration, as it came to be known, wasn't found right away. It took time, patience, and a lot of careful observation. Astronomers were conducting surveys of the southern sky, looking for galaxy clusters. They started noticing something odd. There were way more rich clusters in one particular region than there should have been. If galaxies were spread randomly across the universe, you wouldn't expect to see such a concentration. As they kept looking, kept measuring, the picture became clearer. These weren't just random clusters sitting near each other by chance. They were all connected, part of one enormous structure. The key was measuring something called redshift. When light from distant galaxies travels through expanding space, it gets stretched, making it appear more red. By measuring how red the light appears, astronomers can figure out how far away something is. What they found was remarkable. All these clusters were sitting at roughly the same distance from us. This meant they were physically connected, forming what scientists call a supercluster. But this wasn't just any supercluster. This was a monster, one of the largest structures ever discovered in the universe. Mapping the Shapley concentration required the same techniques astronomers use to study other cosmic megastructures. They measure redshifts to figure out how fast things are moving. They use what are called standard candles, objects with known brightness, to estimate distances. They build three-dimensional maps showing where galaxies sit in space. It's like being a cosmic cartographer, charting territories so vast that our minds can barely grasp their scale. The picture that emerged was stunning. The Shapley concentration is like a massive knot in what scientists call the cosmic web. Imagine the universe as a giant spider web, with long filaments of matter stretching across space. Where several filaments meet, you get a knot, a place where matter piles up. That's what the Shapley concentration is, a cosmic intersection where multiple streams of galaxies converge. But here's where it gets really interesting. What we can see, all those bright galaxies and stars, that's just the tip of the iceberg. Most of the mass in structures like this is dark matter, invisible stuff that we can only detect through its gravitational effects. These dark matter halos surround every galaxy cluster, extending far beyond what our telescopes can see. They're like invisible scaffolding, providing the gravitational framework that holds these massive structures together. Think about that for a moment. Most of what shapes our universe, most of what determines how galaxies move and where they go, is completely invisible to us. We live in a cosmos dominated by things we cannot see, forces we can only infer. There's something both humbling and mysterious about that reality. The influence of the Shapley concentration reaches across incredible distances. By studying something called peculiar velocities, the motion of galaxies relative to the expanding universe, astronomers can trace gravitational influences across hundreds of millions of light years. What they found is that our own region of space, our local group of galaxies, may be feeling the pull of Shapley even now. This doesn't mean we're heading straight toward it. The expansion of the universe and the sheer distances involved make such a journey practically impossible. Instead, the influence is more subtle, like a gentle current in a vast ocean. It shapes the overall direction of motion, but doesn't determine a precise destination. There's something profound about the timescales involved here. The light we receive from the Shapley concentration left those galaxies hundreds of millions of years ago. When that light began its journey toward us, dinosaurs hadn't even appeared on Earth yet. The gravitational influence we feel today, the subtle tug that may be affecting our motion through space, that influence has been acting on us for geological ages. In a way, it's oddly comforting. The universe moves slowly on its largest scales. Galaxies don't race through space. They drift, guided by forces that act patiently over billions of years. Even something as massive as the Shapley concentration exerts its influence gently, like the steady pull of a tide, rather than the sudden force of a crashing wave. The discovery of Shapley changed how astronomers think about cosmic structure. Before, scientists tended to view superclusters as isolated islands of matter, separate entities floating in space. Now we understand that they're all connected, part of a continuous network stretching across the observable universe. This network, the cosmic web, is one of the most beautiful and elegant patterns in nature. On the largest scales, matter organizes itself into filaments and nodes, with enormous empty regions called voids in between. Superclusters like Shapley are the biggest nodes in this web, places where many filaments intersect and matter accumulates over billions of years. It's architecture on a scale that dwarfs anything humans have ever built. Computer simulations help us understand how these structures form. Scientists start with the tiny variations in density that existed in the early universe, just after the Big Bang. Gravity slowly amplifies these differences, drawing matter together along certain paths, creating the filaments we see today. Over cosmic time, some regions become particularly dense, eventually forming massive concentrations like Shapley. Watching these simulations is almost hypnotic. It's like watching frost patterns spread across a window, delicate branches growing and merging, gradually forming intricate designs. The process is slow and steady, guided by simple physical laws, yet the result is breathtakingly complex. The Shapley concentration also helps define the boundaries of our local cosmic neighborhood. Astronomers have identified what they call the local supercluster, a region of space that includes our Milky Way and thousands of other galaxies. The flow of galaxies within this region is influenced by the distribution of mass around it. Shapley, lying beyond our local region, helps shape the patterns of motion we observe nearby. It's like being in a vast gravitational landscape, with hills and valleys determined by where matter clusters together. Our galaxy, along with our neighbors, moves through this landscape, following paths carved by invisible rivers of dark matter and shaped by the gravitational pull of distant superclusters. What strikes me as remarkable is how much we still don't know. Our understanding of these enormous structures continues to evolve with each new survey, each new telescope that comes online. Every dataset adds depth to the picture, revealing previously unknown clusters, refining our measurements of how fast galaxies are moving through space. Future telescopes will undoubtedly uncover even more distant and massive structures, extending our maps of the cosmic web further into the universe. The story of Shapley may turn out to be just one chapter in a much larger narrative about how matter is distributed across cosmic time and space. For now, what we do know is already extraordinary. Our galaxy, along with hundreds of billions of others, moves within a gravitational landscape shaped by structures so large that light takes hundreds of millions of years to cross them. We're part of a cosmic dance choreographed by forces acting across distances our minds struggle to comprehend. And this raises fascinating questions about our place in the universe. If these immense structures shape the motion of galaxies, how fast is our own Milky Way actually traveling through space? What does our cosmic motion mean when viewed against this vast backdrop of the cosmic web? These are the kinds of questions that keep astronomers awake at night, pondering our journey through the infinite darkness. When you settle into your chair tonight, feeling perfectly still, you're actually racing through space at incredible speeds. The sensation of motionlessness is completely real to your body, yet it's also one of nature's most elegant deceptions. Right now, as you listen to this, you're spinning with the Earth at hundreds of meters per second, orbiting the Sun at 30 kilometers per second, while the Sun itself carries you through the galaxy at speeds that would make any Earth-bound vehicle seem frozen in comparison. The question of how fast our galaxy moves, though, isn't as straightforward as it might seem. Speed always needs a reference point, something to measure against. In everyday life, we measure speed against the ground, or against other cars on a highway. But in space, there's no universal ground, no cosmic highway markers to judge motion by. Astronomers had to get creative, and they found their answer in something quite remarkable. The entire universe is filled with a faint radiation, a kind of cosmic afterglow from the early universe called the cosmic microwave background. This radiation comes from everywhere, filling all of space like an invisible ocean. It's nearly uniform in every direction, but not perfectly so. When astronomers measured this radiation carefully, they discovered something fascinating. One side of the sky appears just slightly warmer than the other side. This temperature difference isn't because the universe itself is actually warmer in one direction. Instead, it's because we're moving through this sea of radiation, like a ship moving through water. As we travel, the radiation ahead of us gets compressed slightly, making it appear warmer, while the radiation behind us gets stretched out, making it appear cooler. This effect, known as Doppler shifting, reveals both our speed and direction of travel through the cosmos. The measurement shows something remarkable. Our galaxy, the Milky Way, along with all its neighboring galaxies, is moving at about 600 kilometers per second relative to this cosmic background radiation. That translates to more than 2 million kilometers per hour. To put this in perspective, at this speed you could travel from Earth to the Moon in less than 11 minutes. You could cross the entire diameter of our planet in about 20 seconds. Yet, even at such tremendous speeds, crossing our own galaxy would still take more than 150 million years. Space operates on scales that make even extraordinary speeds feel almost leisurely. The universe has a way of humbling our sense of what constitutes fast and slow, near and far. This cosmic motion isn't random wandering. It's the result of gravity acting over enormous distances, pulling on vast collections of matter scattered throughout the universe. Nearby galaxy clusters contribute part of this gravitational pull. Massive structures like the Great Attractor add their influence from farther away. Even more distant concentrations of matter, like the Shapley supercluster, exert their gravitational effects across hundreds of millions of light-years. Our galaxy finds itself part of a vast network, drifting along gravitational currents shaped by these immense structures. It's helpful to think of this motion not as a single journey in one direction, but as multiple layers of movement, each stacked upon the others. The Earth spins on its axis. The Earth orbits the Sun. The Sun orbits the center of the Milky Way. And the Milky Way itself travels through the space between galaxies. Each of these motions has its own speed, its own direction, its own rhythm. Together, they create a complex path through the universe that no single description could fully capture. The Sun, for instance, orbits the center of our galaxy at about 220 kilometers per second. One complete orbit around the galactic center takes roughly 230 million Earth years. Astronomers sometimes call this span of time a galactic year. Since the Sun formed about 4.5 billion years ago, it has completed only about 20 of these galactic orbits. Since dinosaurs last roamed the Earth, the Sun has traveled through less than one complete orbit around the galaxy. The timescales involved make human history feel like a brief flicker, a momentary pause in the galaxy's slow waltz around its center. Meanwhile, our galaxy and its nearest large neighbor, the Andromeda Galaxy, are moving toward each other at about 110 kilometers per second. Their mutual gravitational attraction draws them together across the 2.5 million light-years that currently separate them. In about 4 to 5 billion years, they're expected to merge, creating a single, larger galaxy. This future collision will unfold slowly, over hundreds of millions of years. Despite the dramatic name, galactic collision, the event will be surprisingly gentle. Stars will pass by each other at such vast distances that direct collisions between individual stars will be extremely rare. Instead, the overall structure of both galaxies will gradually reshape itself, like two clouds of fireflies slowly mixing together in a cosmic dance. These local movements are part of an even larger pattern. Our local group of galaxies moves toward the Virgo cluster at several hundred kilometers per second. Beyond that, the entire region, including the Virgo cluster itself, drifts toward even more massive structures, guided by gravitational influences that span hundreds of millions of light years. Imagine all these motions combined, and it becomes a bit like standing on a moving walkway inside a train that's traveling along a curved track on a rotating planet. Each motion is completely real, but none is directly felt because everything around you shares the same movement. You, your chair, the air you breathe, the building around you, the ground beneath you, all participate in these cosmic motions together. One reason we don't feel these enormous speeds is that motion at constant velocity produces no physical sensation. Only acceleration, changes in speed or direction, can be felt by the human body. The accelerations involved in cosmic motion are extremely small. The gravitational pulls that guide galaxies are gentle, spread over such vast distances that the resulting accelerations are tiny compared with those we experience in everyday life. Astronomers can study these cosmic motions by examining something called redshift and peculiar velocities. By comparing how fast a galaxy appears to be moving with how fast it should be moving due to the expansion of the universe alone, scientists can determine how much of its motion comes from gravitational influences. When these measurements are made for thousands of galaxies, patterns emerge that reveal large-scale flows across the universe. These flows can be visualized like streams or rivers, with galaxies represented as points moving along curved paths toward regions of greater mass. The Milky Way appears as one participant in this vast motion, carried along by a gravitational landscape shaped by clusters, superclusters, and the invisible scaffolding of dark matter that connects them all. There's something quietly reassuring about this picture of cosmic motion. The universe isn't chaotic on its largest scales. It has structure, patterns, and flows that can be traced and understood. Even though the distances involved are immense and the timescales almost beyond human comprehension, the same physical laws that govern the fall of an apple or the orbit of the moon also guide the motion of entire galaxies. It's worth reflecting on how long these cosmic motions take to produce noticeable changes. At 600 kilometers per second, the Milky Way travels about 19 billion kilometers in a single year. This sounds enormous until you compare it with the distances between galaxies. The nearest large galaxy, Andromeda, lies about 2.5 million light-years away, a distance so vast that even traveling at our current tremendous speed, it would take billions of years to cross. This immense scale gives cosmic motion a sense of calm continuity. Nothing happens quickly on these scales. Galaxies drift rather than rush, guided by forces that act patiently over billions of years. In a universe where change often seems rapid and unsettling, there's something comforting about these slow, predictable cosmic rhythms, these ancient dances that began long before Earth formed and will continue long after our sun fades away. The cosmic microwave background radiation, that faint afterglow from the universe's earliest moments, fills every corner of space around us. This nearly uniform glow acts like a reference point, a cosmic compass that helps us understand our movement through the vast emptiness. Without this ancient light as our guide, measuring how fast we're traveling, or even which direction we're headed, would be almost impossible for astronomers to figure out. The Milky Way doesn't hurtle through space in some dramatic fashion. Instead, our galaxy glides along steadily, part of a much larger flow that started billions of years before our sun even existed. This gentle drift connects us to something much bigger than ourselves, a cosmic river that carries entire galaxies along invisible currents. What's remarkable is how this motion reveals secrets about the universe itself. When astronomers measure how fast galaxies move and track their directions, They can actually map out where massive objects must be hiding in space, even when these gravitational sources are too distant or too dark to see directly. Their influence shows up in the motions they create. The Milky Way becomes like a probe, drifting through space and telling us about structures we could never observe any other way. Temperature differences in that background radiation, tiny variations across the sky, work like a cosmic windsock. They show astronomers exactly which way we're moving and how fast we're going. There's something almost poetic about using light from the universe's infancy to understand our present journey through space. Against this backdrop of ancient radiation, our galaxy moves quietly, just one among billions of others, all drifting through a cosmos so old it defies imagination. As scientists continue mapping these galactic motions in greater detail, they're building a clearer picture of how the universe is structured on the largest possible scales. The flows of galaxies, the invisible influence of dark matter, the way massive structures distribute themselves across space. All these elements fit together into one coherent story. This story connects our home galaxy to regions that are hundreds of millions of light-years away, places so distant that their light left them when life on Earth was still primitive. Much of what we know about these immense cosmic structures comes not from seeing them directly, but from indirect evidence. Motions and measurements tell us more than photographs ever could. It makes you wonder what the night sky would actually look like if every obstacle were removed, if dust couldn't block our view, if our eyes weren't limited to such a narrow slice of light. The night sky we see now, beautiful as it is, shows us only a tiny fraction of what's actually out there. Dust clouds within the Milky Way hide vast regions from our view. Our eyes can only detect a narrow range of brightness and color. Even our most powerful telescopes can only capture selected portions of the electromagnetic spectrum at any given time. We're essentially seeing an edited version of reality, a heavily filtered glimpse of something much richer and more complex. If those limitations suddenly vanished, if dust became transparent, and our vision could perceive every wavelength from radio waves to X-rays, if distance itself no longer dimmed the glow of faraway galaxies, the transformation would be extraordinary. The sky wouldn't look empty or sparse anymore. It would appear crowded, layered, alive with structures that remain hidden from us now. The Milky Way itself would change dramatically. Instead of appearing as that soft, pale band we know, it would become an intricate tapestry. Stars, glowing gas clouds, dark filaments would all be visible in unprecedented detail. Those dark rifts we see now, where dust blocks the light behind, would reveal enormous star fields and distant galaxies shining through clearly. What astronomers call the zone of avoidance would disappear entirely. This region, currently hidden behind the dust and gas of our own galaxy, would suddenly reveal itself as another richly populated area of the universe. Galaxy clusters and filaments would stretch far beyond our own stellar neighborhood, forming patterns that extend across mind-boggling distances. Some of these distant structures would still appear faint and small, but others would stand out with surprising clarity. The galaxy clusters that make up the great Attractor region would become visible as dense gatherings of galaxies. The Norma cluster, for example, would appear as hundreds of spiral and elliptical galaxies, all bound together in an intricate gravitational dance. Surrounding these clusters, additional formations would extend across tens, even hundreds of millions of light-years. The sky would no longer feel like a flat dome with scattered points of light. Instead, it would feel genuinely three-dimensional, with structures overlapping and receding into the distance in layers. Galaxy clusters contain enormous amounts of hot gas, heated to millions of degrees. This gas emits strongly in X-ray wavelengths that our eyes cannot detect. If we could perceive that radiation, clusters would glow with diffuse halos, revealing the enormous reservoirs of matter that bind galaxies together gravitationally. The Great Attractor region wouldn't appear as a single bright point, but as a broad luminous area. It would shimmer with the combined light of many clusters, plus the hot gas floating between them. Dark matter would still remain invisible, of course, but its effects might still be noticeable indirectly. Gravitational lensing, where massive objects bend light as it passes by, would distort the appearance of more distant galaxies. They'd be stretched into arcs and rings around massive clusters. If you could see these distortions happening, the sky might look subtly warped in certain directions, as though space itself were gently bending. The most striking change would be the sheer number of galaxies visible everywhere you looked. In a truly clear view, the sky would be filled with them, not just thousands, but millions, each one representing a vast system of stars, some appearing as delicate spirals, others as smooth ellipses, still others as irregular shapes glowing softly against the background. The emptiness between stars that we perceive now would give way to a sense of cosmic abundance. It would be a powerful reminder that the universe contains far more structure and activity than our limited vision normally reveals. The Great Attractor wouldn't look like a single object, because it isn't one. Instead, you'd see a broad region where galaxies become more numerous, where clusters gather more closely together. Beyond that, even farther away, the Shapley concentration would appear as an even richer gathering of clusters, a distant but unmistakable knot in what astronomers call the cosmic web, that vast network of matter that spans the observable universe. If you could somehow watch this sky over extremely long periods of time, another layer of activity would become apparent. Galaxies wouldn't remain fixed in place. They would drift slowly relative to one another, their positions changing over millions of years. The motion would be far too gradual to notice in a single night, but in an accelerated view, the sky would resemble a vast current. Galaxies would flow along filaments toward denser regions, like leaves floating down a river toward deeper pools. This motion reminds us that the universe isn't static at all. The structures we see today resulted from billions of years of evolution, and they continue changing even now. Clusters merge together, galaxies interact and influence each other, and those large-scale flows of matter gradually reshape the cosmic landscape. There's also the question of brightness to consider. If distance didn't dim light the way it does, the night sky wouldn't be dark at all. It would glow in every direction, filled with the combined radiance of countless galaxies. The darkness we see around us results partly from the vast distances between Earth and most of the luminous matter in the universe. Remove that dimming effect, and the sky would shine with a soft, continuous light. Of course, such a sky would probably overwhelm human senses completely. Our eyes and brains evolved to handle a much narrower range of brightness and detail. Part of what makes the night sky so peaceful is actually its simplicity. The gentle contrast between individual stars and the darkness around them. Those quiet spaces between points of light give our minds room to rest and wonder. Perhaps there's wisdom in the way the universe naturally filters itself for us, revealing just enough complexity to inspire curiosity without overwhelming our capacity to appreciate its beauty. When we consider what lies beyond our ordinary vision, the universe transforms into something entirely different. Our eyes capture only a tiny slice of what actually exists out there. If we could suddenly perceive all wavelengths of light at once, the night sky would become a layered masterpiece of information. Radio waves would unveil enormous clouds of hydrogen gas, stretching like invisible bridges between distant galaxies. These gas clouds connect star systems across mind-boggling distances, creating a cosmic web we never knew existed. Infrared light would illuminate hidden nurseries where new stars are being born, tucked away behind curtains of cosmic dust that normally block our view. The universe operates on a scale that makes our everyday problems seem almost quaint. Ultraviolet radiation reveals the youngest, hottest stars burning with intense energy, while X-rays trace the most violent and energetic events happening in space. Each type of light tells its own story, like different instruments in a vast orchestra playing together. This multi-layered view would solve many mysteries that have puzzled scientists for decades. The Great Attractor, that enormous gravitational influence pulling our galaxy and millions of others toward it, would no longer seem so mysterious. Its mass, its structure, the way it shapes the flow of galaxies, all of this would become visible and measurable. There's something deeply satisfying about discovering things through indirect methods. The Great Attractor wasn't found by pointing a telescope at it and saying, "There it is." Instead, astronomers noticed that galaxies were moving in particular patterns, flowing like rivers toward some unseen destination. They had to piece together clues, trace the motion of countless star systems, and gradually build up a picture of this massive structure. This process of discovery reveals something profound about the nature of understanding itself. Every living creature experiences reality through filters. Humans see only a narrow band of electromagnetic radiation, hear only certain frequencies of sound, and perceive time on scales of seconds, minutes, and years, rather than the millions and billions of years over which cosmic events unfold. Bees can see ultraviolet patterns on flowers that are completely invisible to us. Dogs hear sounds we cannot detect. Elephants communicate using vibrations that travel through the ground. Each species lives in its own version of reality, shaped by the limitations and capabilities of its senses. Science has become our way of breaking free from these limitations, at least partially. We've built instruments that extend our perception far beyond what evolution provided. Radio telescopes let us hear the universe. Infrared cameras show us heat signatures across vast distances, and particle detectors reveal the existence of matter we can never touch directly. When astronomers create maps showing the positions of millions of galaxies, something remarkable emerges from the data. Instead of random scattered points, there are patterns. Long filaments of galaxies stretch across space, intersecting at dense clusters and surrounding enormous empty voids. The universe has structure, like a three-dimensional spiderweb made of stars and dark matter. These cosmic web patterns look surprisingly familiar. They resemble frost forming on a window, or the way rivers branch and merge when viewed from high altitude, or even the network of neurons in a brain. There's something almost organic about the way gravity shapes matter on the largest scales. The Great Attractor sits at one of the major nodes in this cosmic web, where multiple filaments of galaxies come together. It's part of a network that extends across hundreds of millions of light years, influencing the motion of everything within its gravitational reach, including our own Milky Way galaxy. Looking at these large-scale maps can be strangely calming. There's an order to it all, a sense that gravity works with patient precision over cosmic time. Nothing happens quickly on these scales. Galaxies drift toward massive attractors over hundreds of millions of years, following paths carved by the invisible architecture of dark matter. This raises questions about permanence and change that philosophers have pondered for centuries. These massive structures that seem so solid and eternal are actually temporary arrangements. The universe continues expanding, and over billions of years, the distances between galaxy clusters will grow larger and larger. The gravitational flows we observe today will weaken and change direction. The cosmic web itself will evolve in ways that are difficult to predict. What we see now is just one moment in a story that began nearly 14 billion years ago and will continue for trillions of years into the future. Our Milky Way galaxy, along with its neighbors, is currently drifting through this vast landscape like a leaf carried by slow-moving cosmic currents. We're part of something called the Local Group, a small collection of galaxies that includes Andromeda and several smaller companions. This entire group is being pulled toward the Great Attractor, but we're also part of an even larger structure called the Local Supercluster. The question of whether we'll ever actually reach the Great Attractor depends on the complex interplay between gravitational attraction and cosmic expansion. Space itself is stretching, carrying distant objects away from each other, even as gravity tries to pull them together. It's like trying to walk towards something on a moving walkway that's going in the opposite direction. Current observations suggest that the expansion of the universe is actually accelerating, driven by something called dark energy that makes up about 70% of everything that exists. This mysterious force works against gravity on the largest scales, potentially preventing many cosmic structures from ever coming together completely. The story of the Great Attractor reminds us that we live in a universe full of hidden influences and invisible forces. Dark matter outweighs ordinary matter by a factor of 5 to 1, yet we can only detect it through its gravitational effects. Dark energy is even more mysterious, known only through its impact on cosmic expansion. These discoveries humble our perspective in important ways. The atoms that make up our bodies, our planet, and all the stars we can see represent less than 5% of what actually exists. We're swimming in an ocean of mystery, barely aware of the currents that shape our cosmic destiny. Yet there's also something inspiring about these hidden realms. Through careful observation and mathematical reasoning, we've learned to see the unseeable, to trace the influence of invisible matter, and to predict the future evolution of structures larger than anything our ancestors could have imagined. The Great Attractor stands as a testament to both our limitations and our capabilities as conscious observers trying to understand our place in a vast evolving cosmos. When we think about our galaxy drifting through space, pulled by invisible forces towards something called the Great Attractor, it's natural to wonder if we're heading somewhere specific. The idea feels familiar, like a long road trip with a destination waiting at the end. Gravity seems to work that way on smaller scales. Planets circle stars, stars cluster into galaxies, galaxies sometimes crash into each other. These are processes we can wrap our minds around, even when they take millions or billions of years. So it makes sense to imagine the Milky Way slowly approaching this mysterious Great Attractor, maybe one day becoming part of whatever massive structure lurks out there. But the universe has other plans. On the largest scales, something else is happening that changes everything. Space itself is stretching, pulling galaxies apart, even as gravity tries to bring them together. Think of bread dough rising in an oven, with raisins scattered throughout. As the dough expands, the raisins move farther apart, not because they're racing through the dough, but because the dough itself is growing. That's what's happening to the space between galaxies. It's not empty void, it's something that can actually stretch and grow. This discovery came almost a century ago, and astronomers have been measuring it with increasing accuracy ever since. What they found recently was even more surprising. The expansion isn't slowing down like you might expect, it's speeding up. Something called dark energy seems to be responsible for this acceleration. Nobody really understands what dark energy is, but it appears to make up most of the energy in the entire universe. While gravity pulls things together, dark energy pushes space apart, making the distances between faraway objects grow faster and faster. This creates a cosmic tug-of-war between gravity and expansion. On small scales, gravity wins easily. Earth stays locked in orbit around the Sun. The Sun stays bound to our galaxy. The Milky Way and Andromeda are actually going to collide someday because their mutual gravity is stronger than the expansion trying to separate them. But on larger scales, expansion starts to win. Superclusters, those enormous collections of galaxy clusters, aren't always held together as single units. Some parts might stay connected, while others slowly drift apart as space stretches between them. So when we ask whether we'll ever reach the Great Attractor, the answer depends on which force is stronger. Current evidence suggests that while we're moving in that general direction, the expansion of space will probably prevent us from ever actually getting there. The distances involved are absolutely enormous, and the farther apart things are, the faster expansion pulls them apart. Over billions of years, galaxies that aren't tightly bound to each other will drift farther and farther apart. Their separation will grow faster than gravity can close the gap. What this means practically is that the Milky Way and its close neighbors will stay part of the same local group, but regions hundreds of millions of light years away will gradually recede beyond reach. The Great Attractor won't become a destination. It will remain a distant influence, shaping our motion, but never fully drawing us in. There's something quietly profound about this idea. Galactic motion is real, it has direction and speed, but it doesn't necessarily have an endpoint. The universe isn't like a closed landscape where everything eventually gathers in one place. It's an evolving, expanding system where some structures merge while others drift apart. Picture a wide, slow-moving river that gradually widens into a vast estuary. The current still flows, but the water spreads out and distant shores move farther away. The motion continues, but the sense of approaching a single destination fades. Computer simulations help astronomers study what cosmic motion will look like billions of years from now. These models account for both gravity and dark energy over immense time spans. They suggest that our local group of galaxies will eventually merge into a single large galaxy. Some astronomers call this future galaxy Milkomeda, combining Milky Way and Andromeda. This merged galaxy will remain bound to a small number of nearby galaxies, forming a stable island of matter. Beyond that island, however, other galaxies and clusters will recede, carried away by the accelerating expansion of space. Over tens or hundreds of billions of years, the observable universe will grow emptier from our perspective. Distant structures will fade from view as their light becomes increasingly stretched and dim. The Great Attractor, even the Shapley concentration, may no longer be visible at all. Their light will be stretched beyond detection. The vast cosmic web we see today will appear fragmented, with only nearby structures remaining observable. This doesn't mean those distant structures will cease to exist. They'll still be there, separated by distances so great that communication or travel between them becomes effectively impossible. The universe will become a collection of isolated regions, each evolving largely on its own. It's almost like cosmic islands, drifting farther and farther apart in an ever-expanding ocean of space. These changes unfold incredibly slowly. The timescales involved dwarf the entire history of humanity. Even the collision between the Milky Way and Andromeda, one of the most dramatic events in our galaxy's future, will take billions of years to begin and hundreds of millions more to complete. The motion toward the Great Attractor, measured in hundreds of kilometers per second, is gentle on such timescales. Over the next few billion years, our galaxy will move only a fraction of the distance required to approach that region significantly. Long before any hypothetical arrival, the expansion of the universe will have altered the environment in ways that make arrival less meaningful. There's also the question of perspective. When we talk about traveling toward the Great Attractor, we're using language shaped by everyday experience, where motion usually implies a destination. But in the universe, motion often reflects the shape of the gravitational landscape rather than a path to a specific point. Galaxies drift along slopes and flows, influenced by multiple structures at once. Their trajectories are shaped by the combined effects of gravity and expansion. Our galaxy's motion results from many influences: the pull of nearby clusters, the broader flow within Laniakea, the distant mass of the Shapley concentration, and the expansion of space itself. It's a complex evolving path, rather than a straight line toward a single object. Like a leaf floating on a river with multiple currents, eddies and tributaries all affecting its journey, time itself plays an important role. The universe is about 13.8 billion years old, and the largest structures have taken most of that time to form. The processes shaping cosmic motion operate over spans so long that entire galaxies can change dramatically while drifting only modest distances relative to one another. If you could watch the universe in fast forward, you'd see galaxies merging, clusters forming, and the cosmic web slowly evolving. But you'd also see the expansion of space gradually stretching the distances between large structures, like dough rising and pulling raisins farther apart. The future of cosmic motion is therefore a balance between gathering and dispersal, between gravity pulling inward and expansion pushing outward. On small scales, gathering wins. On larger scales, dispersal gradually takes over. This perspective feels strangely peaceful. The universe isn't rushing toward a final collision or collapse, at least not according to current understanding. Instead, it's unfolding slowly, with regions of matter forming stable structures while the larger fabric of space continues to expand. So will we ever reach the Great Attractor? Almost certainly not in the literal sense. Our galaxy will continue to move within the gravitational flows of our region, but the expansion of space and the immense distances involved mean that the Great Attractor will remain far away, an influence rather than a destination. Perhaps that's fitting. The Great Attractor isn't a place to be reached, but a reminder of the vast structures shaping the universe, a sign of the invisible mass and gentle currents that that guide galaxies across unimaginable distances. Right now, wherever you are, everything feels still. The ground beneath you is solid, the air is calm, your surroundings are quiet. And yet, gently, almost impossibly, everything is in motion. Earth is spinning beneath you, carrying you eastward at hundreds of meters per second, though the motion is so smooth, it feels like stillness. At the same time, Earth orbits the Sun at about 30 kilometers per second, tracing a path through space. The Sun, along with all its planets, orbits the center of the Milky Way, taking more than 200 million years to complete a single circuit, and the Milky Way drifts through the universe, carried along in a vast flow shaped by gravity on scales, so large they're difficult to hold in mind, all at once. All of this motion is happening now, quietly, continuously, without any sensation of speed or wind or vibration. The universe moves with extraordinary smoothness. There's no rushing sound, no trembling, no feeling of acceleration. Motion at constant velocity is indistinguishable from rest. And so the greatest journeys in the cosmos pass unnoticed by those who travel within them. There's something deeply calming about this idea. The universe isn't a violent place most of the time. It's patient. Galaxies drift rather than rush. Gravity shapes structures slowly over billions of years. Even the formation of clusters and superclusters unfolds at a pace so gradual that entire civilizations would rise and fall without perceiving meaningful change in the sky. When astronomers first discovered our galaxy's motion toward the Great Attractor, it might have sounded dramatic, almost ominous, as though we were being pulled towards something overwhelming. But the reality is quieter and far more expansive. The Great Attractor isn't a single looming object waiting ahead. It's part of a vast gravitational landscape, one feature among many in the cosmic web, influencing motion gently across immense distances, and beyond it lie still larger structures like the Shapley concentration, reminding us that every time we think we've reached a larger scale, there's another layer beyond, another pattern, another flow extending farther into space. It's easy when hearing about these enormous structures to feel small. Our planet is tiny compared to the Sun. The Sun is small compared to the Milky Way, and the Milky Way itself is only one galaxy among billions. On the scale of superclusters, even galaxies begin to seem like grains of sand. But small doesn't mean insignificant. A single grain of sand can still be warm in sunlight, still be touched by the tide, still be part of the shore. In the same way, our small planet is part of the universe in a very real and immediate sense. The atoms in your body were formed in stars long before Earth existed. The oxygen you breathe, the calcium in your bones, the iron in your blood, all of it was forged in the hearts of ancient stars and scattered across space before gathering into new systems like our own. When we speak of our place in the universe, we're not speaking of something separate or distant. We are part of the same story, part of the same long unfolding of matter and energy, shaped by the same physical laws that guide the motion of galaxies. It's comforting to reflect on how steady those laws are. Gravity doesn't change from one day to the next. The speed of light remains constant. The same processes that formed galaxies billions of years ago continue to operate today. The universe is vast and complex, but it's also orderly and consistent, governed by principles that can be understood and described. That sense of order is one reason astronomy can feel so calming. Looking at the night sky, or even imagining the larger structures beyond what we can see, invites a kind of quiet perspective. The worries of a single day, or even a single lifetime, become small against the backdrop of billions of years. Problems that feel overwhelming in the moment begin to soften when placed in a wider frame. This doesn't mean everyday concerns are unimportant. They're part of our lives, just as Earth's motion is part of the galaxy's larger motion. But perspective can make those concerns feel lighter, easier to hold. The universe changes slowly on human timescales. The stars you see tonight will look almost exactly the same tomorrow, next year, even centuries from now. Constellations shift gradually over tens of thousands of years, but the change is so slow that generations pass without noticing. The Milky Way will continue its quiet drift, and the flows of galaxies will continue long after all of us are gone, just as they began long before we were here. There's a certain peace in knowing that not everything depends on us. The universe carries on in its vast, steady way, regardless of human concerns. We're participants in that larger story, but we're not responsible for guiding it. Galaxies don't need our help to move, and gravity doesn't require our attention to continue its work. At the same time, there's something remarkable about the fact that we can understand any of this at all. From a small planet orbiting an ordinary star, human beings have learned to measure the motion of galaxies hundreds of millions of light years away. We've mapped the cosmic microwave background, traced the distribution of dark matter, and discovered structures like Laniakea and the Great Attractor, not by traveling there, but by observing carefully and thinking deeply. That ability to understand, to ask questions and seek answers, is one of the most extraordinary things about being human. The universe is vast, but it's also knowable, at least in part. Each discovery adds clarity, more detail to the picture. Yet, even as we learn more, the universe remains a place of quiet mystery. Dark matter still eludes direct detection. Dark energy remains one of the greatest puzzles in physics. The ultimate fate of the cosmos is still being studied and debated. There's always more to discover, more to understand. Perhaps that's part of what makes the universe feel so inviting. It's not a finished story, but an unfolding one, and we're living within it. Picture the motion of the Milky Way now, drifting through space like a leaf, floating on a slow, wide river. The leaf doesn't control the current, but it's carried gently along, turning slowly, reflecting the sky above. The river moves steadily, not rushing, not stopping, simply continuing on its course. Our galaxy is like that leaf, carried by gravitational currents through the vast basin of Laniakea, influenced by structures like the Great Attractor and the Shapley concentration. All of it part of a larger flow that extends across the universe. Here on Earth, on this small world, life goes on. People sleep and wake, seasons change, oceans rise and fall with the tides, and the quiet turning of the planet continues. Night after night. Under a clear sky, you might see stars shining softly, the Milky Way stretching faintly across the darkness. Nothing in that view would suggest the immense motions and structures we've been exploring. The sky would look calm, almost timeless, and in a way that calmness is real. The universe is not only vast, but also gentle in its rhythms, moving at a pace that allows quiet moments, still nights, and the simple experience of looking up and wondering. The immense scales fade into the background, like a distant horizon barely visible in evening light. The galaxies continue their slow drift. Gravity continues its patient work. The universe continues to expand. But here and now, there is this moment, this breath, this quiet awareness. The vast flow of the cosmos carries everything forward, but it does so softly, without hurry, leaving space for rest, for reflection, and for sleep.